10 in Europe. So we can see here that it's really more difficult for a Global South person to attend only because of the location of these in-person events. And we all know how important it is to be at in-person events, to be able to know each other, make contacts, and showcase our research. And it's super important. If we look at the online events, however, we see that the number of speakers here we looked at, this is mostly webinars. So from the Global South, we are 47 and Global North 61. So this really shows, in my opinion, that the Global South takes the opportunity when given, and it's not like we don't want to participate. It's just that we are not able to go to many events because they are not in our regions. So a bit of history really quickly on the task team. So this all started in the Open Science Conference in Kigali. There was a critical mass of Global South scientists who were didn't really feel comfortable with some of the WCRP, some of the discussions or talks that were ongoing. So the Joint Scientific Committee decided to form a Global South task team. And we started to work in March this year, and we have already submitted a report this May. And if you are interested, this is to be found on the WCRP webpage. And now we are working, we have already a survey draft. We have a really good survey with social scientists involved on doing this survey. And we will also have next year virtual meetings to come together and discuss for a few hours these questions. And we will then come up to the Joint Scientific Committee with recommendations on how they can really include better the Global South in all activities. So this is the team, just to show you like how many countries. It's a big team. We have Moa from APARC, we have Hassan from Cliver, all over the world. Really difficult to coordinate times to have meetings, but anyway, we're doing our best. When we talk about the Global South concept, because that was the first thing we did when we started the team. So how do we define this Global South? There's no real definition. Everyone talks about this Global South, but it's not like there is a clear definition which country is in the Global South and Global North. So we have these kind of loose definitions where we say, okay, these are countries that are greater vulnerability to climate change, less influence on global decision, and less representation in international climate science. And we think that the terms Global South and North capture more the dimensions of the inequality better than just economic indices as the GDP, because it is really about power relationships. Yeah. Okay, so now we're going to go to, okay, let's see how can I do this? Yeah, I'm going to go to the Mentimeter. Let's see. Do you see my slide with the Mentimeter right now?
Yes.
But it's not in presentation mode, right? Now it is.
Yes, so we can see the barcode.
You can see the code, so either you can scan this code. Do you see the code, the QR?
Yes.
So you can either just scan the QR code with a phone. If you want to do it for your laptop, you can go to menti.com and you can put in this code here. So if you can help our people to do that, Hyacinth, please.
Yes. So this code you can scan with your smartphone, and then you see the quiz. Or if you're not holding your smartphone, you can go to this website, menti.com, and then enter this code, 89023756. Have you got there? Or are you getting there?
Yeah, I have 22 logged in right now. I don't know how many people you are in the room.
Okay.
I have 23.
We should be more than 22, so it seems some people are still trying to get in there.
Yeah, we'll wait for a while here. And I'm not sure either if people can of course do this if they are online.
Yes, so certainly everywhere here is on, everybody here can be online because we have internet.
Yeah, but I mean people who are connected by Zoom or perhaps by if people are on YouTube, they can also connect. So I have 27, 28, 29.
We are sending the information. We are sending it.
Okay.
Yeah.
Okay, so we are trying to send to see if we can capture the online participants too.
Yeah, I mean, they should be able, they can also just scan it if they have a smartphone or use the code on their laptops. So it's the same for
Yes.
onlines, really. So I get a lot of hearts here. Thank you so much. And I hope we can start soon. But really want to not leave people out either.
Okay, so can you scan the QR code here with your smartphone? Or with your laptop, you can go to menti.com and enter the number on top.
Okay, so we have been at 36 for a while. Do you expect more people to join? Yeah, 37,
Okay.
38. How many people do you
Can
think?
you see the QR code?
Okay, so perhaps the online people
You
are.
can go to menti.com,
Mm.
menti.com, and then you enter this code.
So I have 41. If someone is still struggling, perhaps you can tell me by the
Yeah,
chat of Zoom.
maybe a few seconds, one or two persons still
Okay,
trying.
excellent.
Okay, have you got that? Yeah. Okay. Yeah, so Anna, I think we can probably move on.
Okay, excellent. I have 48 people here. So let's go to the first question of this Mentimeter, which is, do you self-identify as being from the global south, from the global north, or none of them? So here you can see on my screen what people are replying. And I will wait until we get about 49 answers. So I have 30 out of 50. So if anyone has a problem to, like technical problem to reply, perhaps you can put them in the chat or talk directly to Hyacinth.
So does anyone have problem voting?
I mean, it can be difficult, or perhaps you don't want to reply, but just if someone has technical problem, it's good to be able to resolve.
Yes. Yes. Okay, so we're at 35
Yeah, I
votes.
think we can go to the next one because perhaps there are people who doesn't want to reply to this question. And that is okay. Okay, so next question. Explain in a single sentence why you self-identify as being from the global south, from the global north, or none of them. And of course, here is also the place, if you didn't like the question, the question on the other slide, you can tell me why you didn't like it. So the question is, explain in a single sentence why you replied as you did to the question on the other slide. So why do you identify as a global south or a global north, or why did you define as none of them?
Okay, so the replies are coming in.
Yeah, exactly. So we can see some replies are coming in here on the screen. Oh, so really, really interesting replies are coming in. So there's very interesting and diverse replies coming in here. For example, I can also see that it might not be known to everyone the terminology Global South and Global North, because someone had to check online to know what the terms mean. So that means that it's not a terminology that everyone is aware of. So that is really good to know for us in the team. Less or no equal opportunities, less represented on scientific and political assembly, third world country, sub-Sahara. Yeah. Super interesting replies, and so thank you so much for engaging with this. So do we have someone who hasn't replied yet who wants to reply? If you're there in the room, you can raise your hand if you're not done yet. Otherwise, and you can tell me, Hyacinth, if anyone is raising their hands.
Yes, so no one is raising their hands here.
Okay.
I think we can probably move on.
Yeah, we can move on. I can say in 30 seconds.
Yeah.
Because I just saw a new answer coming in. So in 30 seconds, I will move to the next slide. Less research support from my institutions and the government, poor infrastructure and support communities, poverty. Yeah. More vulnerable to climate change. Okay, so thank you so much. We will need to move on. Okay, so one thing that we are doing with the task team, that we are trying to identify, since we want to have better inclusion of the Global South in the World Climate Research Program, including APARC. We are trying to understand what the barriers for Global South researchers and students are. So this is a question where you are going to rank to what extent you identify with the following statements. So 1 is I don't identify at all, and 5 is I identify completely. So the first statement is engaging internationally in my area requires self-funding to attend to meetings which I don't have access to. So if you agree, you put a lot, you put a 5. If you always have your own money from your institution, you can put a 1, for example. I have been prevented to attend to an international event because of visa issues. At international events, in person or virtual, I have felt not good enough or too uncomfortable to express myself or share my opinions. So we have quite a lot of replies. I will give you 1 more minute to fill out. If you have any technical problems, you can tell me in the chat or let Hyacinth know. But otherwise, I give you 1 more minute to fill it out, and then we can have, I will ask you if you want to, if anyone wants to share anything around these questions. Okay, so I will close this. Or actually, we can keep it open because just what we could do is to see if we have anyone who wants to share about experiences or make a question to me or anything from in particular for the online or the Zoom participants.
Does anyone wants to say something? Yes.
I just want to ask, is it our question, is it related to this question or?
Yeah, like anything. I mean, I just answered.
A testimony, like regarding this situation?
Yeah, I mean, I just want to, if you have a comment on these questions, you're welcome to do that comment. Otherwise, also, if you have a question or a comment on something else related to the Global South, welcome.
No, I just want to comment regarding the fact that most of the Global South, like particularly in Senegal, some of our team faces some kind of visa issues regarding the attendance for international events. So that's what I want to add, that this case are really happening here in Senegal. So that's it. Thank you.
Yeah, thank you so much. Anyone else who want to comment?
Okay, thank you. One more thing is oftentimes the timeline between invitations and the actual meeting actually limits most people from the Global South, speaking with reference to Nigeria in particular. Before they could do all the visa processing, oftentimes the time is short. So it actually limits us from engaging in some of the meetings. Then also the cost of internal travels, especially if your research station is quite far from the international airports, the logistics involved and the other challenges actually impede on the desire to engage in international travels among most researchers. Thank you.
Thank you so much. Yeah, it's really an important issue that sometimes perhaps one could get a visa if there only was enough time. Yeah, that is something that could be addressed easier than other things, of course, to have better planning. Thank you. Any other comment? If not, let's see if someone no one, I think no one is raising their hands in the online. So I will go to the next slide if we don't have any other comments. So
Yes.
here we will spend some time because here the question is, which other barrier have you experienced when engaging in the international climate research community? So here you are free to think for a couple of minutes to write down what other barriers, what other problems have you had when
About it.
engaging in
About it.
yeah,
So,
language?
that.
Totally.
Paste it there. The Eldoret. So it's Eldoret. Nature and culture.
Yeah, can you mute yourself, please?
Right.
Can you?
So we get a good or clear image for that.
Someone is actually talking that is not supposed to be speaking. Can you mute yourself, please?
Probably Muhammadu should be able to
Right.
mute as well.
Nature and culture.
Yeah, can you mute yourself, please? Can you?
Right. So we get a good or clear image for that.
Someone
To upload that image.
Okay, go ahead. Yeah.
Okay, so really interesting things are coming in here. So I will give you another 1 or 2 minutes because we have almost half the people have replied. You can also reply several sentences if you come up with something else. And what we will do after stopping this the entering of the sentences, we will vote. So you will be able to see all the statements on your screen, and you will be able to vote for like vote up things that you agree with, but you didn't put yourself. So still have some more replies coming in here. So in the sake of time, I have to stop in 30 seconds. So if you haven't entered yet, please try to do so. Okay, so I'm going to stop the entering of new messages. And now you should, please tell me if you don't, but you should be able to see on your screen like all the statements that were put in this question, and you are going to be able to vote for 3 of them. So if you find 3 statements that you do agree with, you can vote up for them. So we will see which agreement has most votes. If someone else have experienced the same barrier as you. Okay. So I think it works like you put in 3 and then you submit the vote. I don't know, is it that it is, does it look like this on your screens? Oh, let's see. Okay, so I know it's a lot of statements to read, especially if English is not your first language. So I will give you around 2 minutes more to be able to vote properly.
That's fine.
So we have about half a minute left to vote before we need to continue. This is the last question, but I will see if we want any comments from the floor, I will take them as well.
Okay.
Yeah, I'm waiting a few more seconds, and then I will display the results of the voting on the screen, so you can see the results. Okay, so I'm going to close now. Okay. Okay, so we see we have technology and funding. Language is a big issue. Data sets, computing resources. Less information about the topic since I have a different background. Funding, administrative delays, visa denial, administrative burden. I don't have a mentor. It would be really so thank you so much for giving this excellent input and also for voting. Does anyone want to comment on something that they voted for or that they wrote?
Any comments on the voting or on the issues? Yes.
The comment I would like to give in this poll is regarding all the questions we face. Our main issues in the global south is funding. So even we have visa issues. So, but for example, if we can have, for example, all the administrative processes, I think visa will not be a problem to get. So the the main problem is funding. So that's why if we look at or we can notice that funding is the popular problem for global south.
Okay.
Yeah.
Then we have another feedback here.
Yeah.
I would like to add also regarding the funding, and here in Senegal, most of the cases, like if students have collaboration with all other countries, like international collaboration during his or her PhD, he will defend his PhD or her PhD faster than someone who did not have that kind of collaboration. And the administration is faster and things go like faster in everything if there is kind of collaboration. And if you compare that student with another one who did not get funding, his research take longer and slower. Yeah, thank you.
Yeah, I totally get that. That's
Thank
a
you.
really good comments. Anyone else spontaneously there, or?
Does anyone else want to give a feedback?
I was interested in one particular which says, I don't have a mentor, and 4 people voted that up. I don't know if someone wants to add on because it seems like I think that you that who are participating are most early career students perhaps in this training. So perhaps they
Yes, so
feel that there is a lack of senior scientists who can mentor.
we have a hands up on that.
Okay, great.
I think all of us know these challenges. My question is how to overcome all of these.
Yeah.
You wanted to talk about the mentorship.
Yeah, we also what I think what can be done, we are working on how to make this better within a particular organization, which is the World Climate Research Program, which APARC, who is organizing the workshop that you are in, is a part of. So of course, from the organization WCRP, we will not be able to change like any structural thing of the world, unfortunately. But what we can do is to give recommendations to the WCRP. For example, if we know that people need more time for visa applications, or for example, if visa is an issue, perhaps we can try to make events happen in countries who doesn't have that high visa requirement. Also, in terms of spending, we could spend funds in a different way. If we have funds, we can try to allocate them in a way that suits the Global South better than it does today. And also, we want to we think it's really important that the Global South has an impact on the research agenda and priorities of the World Climate Research Program, because there is because we have some specific questions that we might need to address in the Global South that are not on the research agenda. And if we can get those issues out by having more people that are really engaged, that can be like some sort of solution. But we are still trying to work on the solutions, of course. And if you want to contribute to replying to a longer survey, well, it won't take this long because now we're doing the Mentimeter, but I would like to share just another QR code with you, which is this one, because here in this, if you would like to help us to come up with recommendations on how things can be easier for you to participate in international WCRP events, you can scan this code and you enter your email and your name. And as soon as we have the survey ready, we will send it to you. And we are also interested in interviewing some people. So we will do like interviews, like meeting virtually with people. And of course, everything will be totally anonymized. We will also be organizing virtual workshops, like I mentioned before, like next year we will have a series of opportunities to come together and discuss this question more in depth in really small groups, like, I don't know, 3 to 5 persons perhaps, and then share with these insights also, so that we can build on that when we are doing the recommendations. So please, if you would like to contribute, you scan the code or you go to this direction. And thank you. Now we are running out of time. And so I want to thank you so much for engaging in this activity. It's super important for our team to have your input. And thanks also to Mohamedou, who was so kind to let me have this space at your workshop.
Yeah, thank you very much, Anna.
So Moa, I will share the slides with you, just if anyone didn't get the QR code, and they can ask you perhaps.
I mean, we did not get to send all the information to the old application online. I think Maria just succeeded to send at least some of that's why the online wasn't probably participating to the.
Yeah. So yeah. So let's get in touch on this so that we can get out information on the survey to more of the participants. Okay. So thank you so much. I will disconnect now because you have another lecture coming up, right?
So but I hope that this would not. And I mean, for contributing also training school. Thanks so much.
The rest of our program for the day. So I think I'm the next speaker.
Yeah. C'est bon. C'est bon. C'est bon. Okay, the next speaker is Professor Hasient from JOMA at Germany. He will talk to us about the introduction to climate system modeling. Professor Hasient, the floor is yours now. Maybe you can introduce yourself and.
Yeah, so thank you very much. And everyone, thank you again. So presently I work at JOMA in Germany. Originally from Nigeria, I still hold academic position at the University of Nigeria. So I'll be talking today briefly about climate system modeling, like the traditional thing we do as climate scientists, which is kind of a bit different from the AI, which is a topic of discourse, but it's like the basic physical science foundation. Okay, so I understand my time is very small. I'll try to keep to that, but just to give a kind of a summary or a highlight of the topics that I'll cover in this talk. So I'll talk about the climate system, the components of it, and the time scale or their response times. Then definition was already done yesterday by Victor Ongoma, who gave a talk virtually. And then I'll talk about, after this bit of background, then I'll talk about climate modeling, like how you construct a climate model, and then a brief 1 slide or 2 slides of history. And then I'll go to IPCC, to introduce again climate change, and then go to the IPCC reports. So I just look at my time and pick what I consider the most important thing. I hope it works.
Can you mute yourself? Can you mute yourself?
Huh?
Can you mute yourself?
My video? Oh, myself. Oh, sorry. Yes. I'm not sure that's in the start video. Yes. Okay, so we get going. Okay, no, so now the climate system, basically we have several spheres. You can already see them, the atmosphere, the water in the ocean or in the rivers or in the lakes, then the frozen part of the earth, the cryosphere, and the living part of the system. And then of course there's the land surface or the lithosphere. And what is really important is, like, you see the connection, like arrows going in both ways, connecting all of them. So that basically speaks to like very strong interactions from one part of the climate system to the other. And we can show that interaction a bit more. And so what we have here is a bit of illustration of the connection. Like imagine this is the ocean here and there's atmosphere, and you can have, let's say, evaporation of water going from the ocean into the atmosphere, forming cloud, and then precipitating as rainfall back into the ocean or sea ice. So there's very strong coupling between these different components of the climate system. And so the next thing is the different processes that these interactions give rise to have like different time scales or different response times. So something like turbulence can happen like in matter of seconds, and the scale, it's a bit of a linear connection between the horizontal scale of the atmospheric process. And then on the vertical here is like the time response time. So from turbulence to something like the monsoons, like we get rainfall over most of West Africa from the monsoons. So we have like rainy season, which is like 3 or 4 months, depending on where you are, or a little more. The system moves into our locations, and then after that, it moves away. So this is something that has a time scale of like, repeats like every 1 year, and so on and so forth. So this is for the atmosphere. So for the ocean also, you also have like different time scales again, from turbulence to something like El Nino. We'll talk a bit about it later on. That happens, repeats again after 3 years or 4 years or up to 7 years. And then for the cryosphere also, you also have like different time scales. So what you have up here is like definitions of the different things. And then under here, you have like the kind of some indicative time scales. So for example, snow, the time scale go from like a day to several months. So imagine a snow can fall and melt within the same day, or can persist over up to a season or so. To the ice sheets that have like time scales up to 100 years, up to a century, or even a millennium. So there's just multiple processes, multiple time scales within the climate system. Okay, so definitions, again, Victor already did this yesterday. Since we are in the house of mathematicians, just to say, one easy way to understand what you're talking is like you have a distribution here, a statistical distribution of climate values, and then there's a kind of a shift. So here, you imagine this is temperature, you're shifting to the right here, so you're getting from colder to warmer. It could be in this direction also. Then climate variability, it's really like a kind of a very important part of it. And so in fact, most of us that study climate science, what we study is climate variability, not the mean climate, because you already know what the mean climate is, okay? So we really want to know how the climate will fluctuate. I wouldn't want to say change. For example, this year, well, the rainy season is already gone. Or next year, are we expecting a lot of rainfall during the rainy season? Are we going to expect less? And so on and so forth. So we have like different modes of variability. So these modes are like some clearly defined patterns or clearly defined behavior of some aspect of the climate. So for example, El Nino is the big one here. So this is defined by sea surface temperature here, which you see that develops over the eastern and then to the central part of the Pacific Ocean. So this basically changes atmospheric circulation globally, and then affect climate of practically everywhere, including our own location here. So there are several of these modes of variability. There's also NAO, there's also the Atlantic AMO, or the Atlantic multi-decadal oscillation. So, and the time scale is like a bit of 3 to 7 years or so. So the AMO, the time scale is multiple decades. So up to 50 years, by 5 decades to 70 years. So it really takes time. And this is very important for our region. This is where we are, right? So what you have here is warmer than normal sea surface temperature that persists over several decades, okay? So when you do this, what you are basically doing, this is warmer, this region becomes warmer than this region. So what it basically means is that the ITCZ, that is the rainfall belt, the rainfall and convection belt to basically move further north to its usual latitude. So what this will imply is in our region, we get more rainfall than usual. So imagine if this is reversed, so this becomes cold. It also means that the rainfall will go to the south, and then we are going to have less rainfall than we should have. Okay. So I started with like a kind of the short form to the multi-decadal. So now this is the very long version of climate variability. So the so-called Milankovitch cycle. In a nutshell, tries to relate the changing connection between the earth and the sun, because all the energy for the climate that drives the climate is from the sun. So what it means is that if you change the relationship, for example, if this earth becomes slightly closer to the sun or further away from the sun, the energy input from the sun will change, and that will affect our climate. So, but this cycle takes like hundreds of years or thousands of years. So this is like really the very long version of climate variability, if you like. So, and there are examples of these different parameters connecting the earth to the sun. This is one of them. This is another one, and then this is another one. They have different time scales. So if you put everything together, you are going to see a connection between all these parameters and the solar forcing. That's basically what I tried to say. And then at the surface of the earth, you can link this to the temperature, to the air temperature. This is reconstruction. So if you look at the earth, so it's like 1,000 years, so it's really a very long version. So you can see like a very big jump in temperature, decline in temperature, depending on how all these join together. And so if you look into the recent past, so there's also like a lot of argument. Do we really have climate change, or this is just the normal Milankovitch cycle? So, because if you see we are coming from a very cold place into a very warm place at the present. So ordinarily, even without anthropogenic emissions, we're actually coming out from a very, very cold place to a warmer place. And this is basically natural variability, the very long version of natural variability. Okay, then another thing you need to be aware of, even though I'm not going to discuss it in details here, is climate feedbacks. So feedbacks within the climate system, like you have a cloud, how does the cloud respond to radiation, and how does it affect the climate? Or you have ice or snow, you are basically changing the surface. And if you change the surface, the connection to solar radiation and every other thing is going to change. So this is also really a very big topic, like in climate science or in terms of climate modeling. So you just need to be aware of it. Something going wrong here. Oh my God. Something. New session. Put light down. So in reality, we are back to the definitions again. Climate change and variability are kind of very mixed. So what I show you here is the trend of sea surface temperature, or surface temperature actually, over land and over the ocean. So from 1981 to 2020, So you basically see warming everywhere. So that's what we hear about global warming and all that, right? But that is for the entire globe if you take an average of this globe. But if you look at specific places, our place everywhere is basically warming, right? But if you look at the Pacific, you see even cooling, though not statistically significant. Then over the North Atlantic, over the Southern Ocean and all that. Okay? So you don't see any warming there, or you don't see significant warming there. Some places even cooling. So what this basically points to is the role of internal variability. That is the natural variability of the climate system. So everything is kind of actually mixed when you have observations. And okay, back to the topic. What I've tried to do is to give you a few minutes introduction to climate science so that now you have arrived. Let's talk about modeling again. So why do we model? Many reasons. We may want to understand processes. We may want to predict, which is by the purpose of science, to understand things so that we can make some predictions. So we can be predicting the weather, or we can be predicting the climate into the next 10 years, next 100 years, as the case may be. And we also want to know the uncertainty, like they kind of calibrate our prediction. So how sure are we? How much spread we have? How much do the models agree? Or the simulations, as the case may be. So in a nutshell, climate modeling basically means we have a globe, and then we have like kind of a mesh point where we can calculate our equations. So we try to represent the physical processes that happen in the climate system, okay? The interactions that happen in the climate system on these points on the globe. When we do that, then we can try to simulate, to reproduce what we are measuring. So we have measurement points all around the world. So we try to simulate the climate, and then when we are sure we can simulate the climate, then we can now use it to make prediction into the future next 100 years, 50 years, and all that. And this is important for a whole lot of things that we need. Okay, so this is maybe the take-home message. And to do this, a number of things are required. Number one, we need some initial states. Okay, so you want to predict into the future, so there has to be a time zero where you are starting from. So you need measurement at that particular point in time. So like the initial conditions for your model. So you start from some measurements. So you can simulate from anywhere to anywhere. You can simulate from today. You can simulate from 100 years ago. But you need a measurement for that 100 years ago to start from that point to move. And then, of course, some boundary conditions. So assuming you have an atmospheric model, so the ocean or the land surface is like your boundary condition. So the environment in which your model is going to evolve, or some external forces like greenhouse gases and all that. So if you have an ocean model, then the atmosphere is like your boundary condition. So the environment, you impose an environment on which the ocean is going to evolve. Then if you have a coupled system, then external forces like greenhouse gases and aerosols. Okay, then you also need a number of equations, a close set of equations to relate atmospheric motion to temperature, moisture, pressure, and all that. And then a method to integrate your model forward in time, and computing power, or hundreds or thousands of people with papers solving the equations and passing to themselves. And I promise you, they're going to end up with very wrong results. It was done in the past, and it ended up in very huge errors. Okay, so you must need a very big computer. Okay, so what is climate modeling? Well, in a mathematics institute like this, they'll think it's a very simple thing. Just solve Newton's, just solve the momentum equation, just equation of motion for zonal advection, and then a few other things, and you are done. Yeah, well, when you do that also, you need the thermodynamic equation. So we can talk of a few governing equation that is the heart of climate model. So one of them is the conservation of momentum, and then the thermodynamic equation, conservation of water vapor, mass conservation, the ideal gas law, and then the hydrostatic equation. So when you put all these things, I have to again say that the climate models we have as of today, they are not Python codes, they're actually Fortran codes, mostly, then a few of them are in C. Maybe there are some toy, very simplified models that are in Python or interpreted languages, but if not. Really? Yeah. I know that trying to relate the icon model in Python. Yes, I am aware of that. Yeah. I learned because they are co-developing this with Max Planck in Hamburg. So I also listen to them sometimes, like they really want to translate it to this. I'm not sure if it's operational yet. Okay, so when you do this, you are going to get, okay, I have to check my pen. Okay, something that is very interesting like this. And sometimes it can help us to even discover things that we are not aware of or has not been measured. So if you focus on where we are, you can see, and this is like winter time, like around this time to January or so. So you can see the influences. This is water vapor column integrated. So you can use it as a tracer for circulation, for example. So you can see a kind of advection from here, which is warmer, that hits Senegal. And then you can also see from the north sometimes, so you can understand why you may have kind of it's cold, or no, it's warm or something. Okay, so since we're in this class, just a few take-home messages. So one of that is prognostic versus diagnostic variables. So those ones that you can solve directly from the model equations are what you call the prognostic variables. So the models directly predict them, but then there are a whole lot of other things that are of interest that are not solved directly from the governing equations. But you can derive them. So those are the diagnostic variables. And then another thing that is also of interest to you, I believe, or you should know, is what we call dynamics and physics. So dynamics, I give an example here. Why is this showing? Okay. What? Yes. So what climate science people call, when you hear them say when they say dynamics, they're basically talking about the processes that you can actually represent in the model, whether they are prognostic or diagnostic, but you can actually represent them in the model. Then there are processes like friction or diffusion, or that you cannot actually represent fully in the model. So they are parameterized. So you use the things you have to kind of, or they could be empirically derived. And this is where something like machine learning will come in, or I think people are trying it a lot. So that's basically model physics. Things you cannot resolve, like cloud. The clouds are very small. the spacing between the points where you are solving the model equation is maybe 100 kilometers apart. The horizontal scale of a cloud is like a few meters or a few kilometers. So you cannot resolve it. But you can use other things to know, like the total effect of the circulation or the connection between them. So that's what the physics. 5 minutes? Yes. Some total or a kind of total understanding or some empirical relations you can expect between some variables to predict another one, because you cannot resolve them completely directly. Okay, so a brief history. So this started like in the late 60s, 70s, and then with the atmosphere first, the development, and then there was coupling up to land. So land surface model basically mean you have the equations I've shown you for the atmosphere. And I have to say also, you also have the same motion equations for the ocean. Assuming a lot of things will change, of course. Then there's a land surface model. And then there's also a coupling to the ocean in the 90s, ocean and sea ice. And then up till today, when we have like atmospheric chemistry, carbon cycle, biogeochemistry in the ocean and all that. So, I mean, the climate system model has really advanced. So we have the models that have become more complex and more processes presented. So that will also mean more expensive to run, like more computationally expensive to run. Okay, another part of the history, the development of climate modeling and all that actually won the Nobel Prize in Physics in 2021. An example of that, coupling is an in-house model at JOMA where I work. So they have ECAM for their atmosphere, then there's a chemistry model that is coupled to it, and then the land surface model that is coupled to it also. So these three are for on the atmosphere model grid. And then there's a coupler, OSIS, that connects to the ocean model NEMO here that can be nested. And then there's also CIS model and biogeochemistry model. Okay, so in the last few minutes, IPCC reports, latest one was published in 2021. A new one is already being in the works now. I don't know, maybe in 4 years or 5 years, another report will come out. And I don't have the time to explain what climate change means from a simple physics point of view, but I just leave materials here in case you're interested. And I just go modeling centers, not in Africa at the moment. It's also a history of the modeling centers. So just to, in summary, to explain natural variability in the climate system. So like I explained, there's a lot of natural variability, the ups and downs, okay? So this is like greenish shade in here is like where you use only natural variability to drive the model. And then this one here is where you include human emissions in the model. And then the black one here is the observations. So the point is that without human emissions or human caused climate change, what we're going to have is this. So this is going on because of the influences of humans. And in a nutshell, that will mean, so when you have excess heat in the climate system, it's stored in the ocean because the heat capacity of the ocean is so much more than that of the atmosphere and a lot of reasons. So all the heat, most of the heat is basically stored in the ocean. And when you do that, the sea is going to expand from a simple way to understand it, right? Warmer, expand. So you get sea level rise. Of course, the sea surface temperature warm. and then you lose glacier, and then rainfall changes, and all these are mainly driven by greenhouse gases such as CO2. So the scale here shows you how this has been evolving over the years. And yes, so this is my last slide. Thank you very much.
Thank you, Professor Hyacinth, for your nice presentation. Do you have questions for Professor Hyacinth? Yeah. Oh, we are running out of time. Let us just take 2 questions. Okay. Okay. And then later you can ask him the further question. I think you were the first one to ask question, right?
Okay. Thanks. Okay, thanks for this presentation. My question is about the climate modeling. For me, the question of the future of climate modeling. If I noticed actually I can say the Moody's, the data-driven model, it's a little different by the climate physics model. My question is the future of climate model, physics model. You think that it is the climate modeling with the physics based, we will continue, or we will replace by the data-driven model? It's my question. If it's possible to think about this, or we can go.
Yes, actually, the future of physics model is kind of guaranteed. From what we know today, the data-driven can be useful, like in terms of parameterization or in terms of refining the models, but you still need to solve the physics equations. For example, if you want to project to the next 100 years, I don't know what you are going to use to train your data-driven model or something. So maybe for the next foreseeable future, I think they can go side by side. Yeah, so, and people who actually train in this physics model don't take the data-driven model seriously, because this can actually solve the equations and you can see the motion of the particles or whatever and all the details. They don't think that this is a substitute, but they can go together.
I'm agree. Yeah, I think the climate modeling is very good, and the statistical modeling, we use it actually. It is good now, but we have a challenge. Challenge is the climate change. The climate change every time, and when the climate change, we don't have input to managing your model or your tools to have a good forecast, I think. Understand me? But the question is, actually we use the dynamical model. Actually, we use it in our service.
Okay.
Yeah, and we use also the statistical modeling, and I think the dynamical modeling is very good actually, and the statistical modeling is good, but also we have a challenge. Because you have a climate changing every time, and when you have a climate change every time, you don't have a very good input in your model.
Okay.
Yeah, it is my.
So in that way, so sorry, I have to recalibrate my answer. So in terms of like weather forecasts, like next few hours or something, maybe the statistical models or the data-driven models will be more useful. But if you are talking like in terms of very long-term climate, where you need like because if you need to predict the weather of Senegal, of Dakar in the next few hours, you don't really need to care about what is happening in the ocean or in the sea ice. But if you're talking about long-term climate change, that matters.
So sorry guys, I'm seeing a lot of hands up, but it's time, and we will have time during the breaks to discuss about those questions. Yeah, we can take online because they don't have the opportunity to. Okay. Rahmaja was asking, how can quantum computing realistically contribute to climate modeling and combating climate change?
Yeah, so that is speeding up computer. So there's actually, I can't remember what it's called, but there's actually a graph which I should have included here that shows like how when you increase computing power, how fast the climate models will go. But you see, as time goes on, they have become even more complex now, so that even the advances in computing doesn't really speed it up again. So it's like we are at a crossroad now. Yeah, I can't remember this, but there's a very popular plot that shows how this grew from the 70s, but in recent time we are not getting any much improvement. So you have to wait out the time. Thank you.
Okay. Thank you very much, Professor Hyacinth, for presentation. And now the next speaker is Professor Jonathan from Tsinghua University in China, who will talk to us about atmospheric reanalysis products. Professor Jonathan, are you with us?
I'm with you. Yep. And I have to thank Hyacinth for really laying the foundations for a lot of what I'm going to talk about. So there will be some common overlaps, and as I'll point those out when they come up. All right. So the focus of this talk is atmospheric reanalysis. I think many of you are using reanalysis products in one form or another. And so I think it's helpful. There is a lot of confusion, or has been a lot of confusion about what exactly goes into reanalysis, what it represents, and how not to use these products, right? And so I'll start with what a reanalysis is. Right? So this is a best guess of the previous state of the atmosphere. And I think it's also helpful to indicate what a reanalysis is not. The reanalysis is not observations. And so if we think about what actually goes into a reanalysis, the first and foremost component of any reanalysis is a model. Right? And so there's a forecast model, which has physics and dynamics, just like we have seen in the previous talk. There's then a data assimilation system, and that's where the observations come in. So the reanalysis is constrained to follow along with observations, but as it takes in the information from the forecast model and the input observations, it tries to take account of the uncertainties and the errors in both, right? So it will follow the forecast model trajectory relatively closely as well. And so the first component here is the model. And in this case, this is usually a very well-tested, earlier, older version of an operational weather forecast model. So like the ECMWF IFS or the NOAA GFS, these are both forecast models that are used in current atmospheric reanalysis products. Because we want the reanalysis to be very stable in time so that we can use it as much as possible for climate studies, the model itself is fixed over the lifetime of the reanalysis. And so that allows us to attribute any changes in the state of the reanalysis to other components like climate change, but also to the input observations. And so we have just seen the different components that go into the model. I'll come back to this a little bit later on, the dynamics and the physics, as well as boundary conditions and forcings, and a coupled land surface model, and possibly a coupled wave or ocean model in some cases. The second component is the observations. And so a lot of times we can classify reanalyses according to what observations go into them. The summary analyses like 20CR or ERA 20C, they only bring in information from surface pressure and winds. The advantage of that is it allows them to go much farther back in time, into the middle of the 19th century in some cases. But the disadvantage is that they don't have any observational information in the upper atmosphere. And so as you move away from the surface, the constraints on the state of the system get weaker. We can also add conventional input, right? So there are a couple of reanalyses like this, JRA55C, and a new core reanalysis that's been produced by NCEP, which I'm not sure, I don't think that's actually available yet, but it will be soon. In this case, we also add information that's taken from direct observations from aircraft, direct observations from balloons, and so on. And the advantage of this is, again, that you get a more stable system over time, because the biggest changes in the observing system are in the next type of observations, the satellite data. But the satellite data also give you the strongest constraints on the observed state of the atmosphere. And so a full input reanalysis like ERA5 or MERA2 includes satellite data in addition to those other products. The quality and quantity of the observations that go into these systems can vary quite a lot in both space and time. It's also important to recognize that the assimilation space is not necessarily the same as the variable space. And so when we bring these observations in, we try to apply also some physical constraints like geostrophic balance on the assimilation increment or various other types of constraints that can help us to keep the reanalysis stable and physically realistic. The third component is the data assimilation system. So older reanalyses like NCEP NCAR or JRA25, they would use a relatively simple assimilation system, which is called a 3D variational. What that means is that the information would only be ingested into the reanalysis at certain times, and it would be ingested in a chunk. The problem with that is that when you do that, you can potentially introduce some instabilities, right? So you get warm air under cold air, for example, and that can then lead to spurious wave activity. And so more recent reanalyses like ERA5, JRA55, JRA3Q, they're using a four-dimensional variational system. And what this does is it takes into account the time that the observations were taken as well. And then it tries to match the full trajectory of the forecast model over that time window, as opposed to only the state at a particular time. Only a few variables in the reanalysis are directly impacted by the data assimilation. This is also important to keep in mind if you're using reanalysis products. Things like temperature and specific humidity and winds are directly impacted by the assimilation. And so these are more likely to be consistent with observations. But if you look at other variables like cloud fields or radiation or precipitation, these variables are only indirectly constrained. And so as a result, you can't necessarily expect those to match the observations well. A few guidelines for using reanalyses. So recent products tend to perform better. And so generally we would discourage any use of the older reanalyses like NCEP NCAR or NCEP DOE. And to give you an illustration of that, right, so here we can see this is for the stratospheric circulation, but I think the illustration is quite clear. On the right-hand side of this table, these are the earlier reanalyses. And on the left-hand side of the table, these are the more recent reanalyses. And the green colors indicate greater consistency with observations or with physical expectations. And the red colors indicate that we don't think this reanalysis is useful, scientifically useful at all, right? And so the more recent reanalyses are generally preferred. I'll show you some counterexamples to that though later on. The second thing you need to be aware of is that if you are looking at reanalysis products for long-term variability or trends, you need to be very cautious about drifts and jumps or discontinuities in the data record. And so for example, in 1998, 1999, there was a transition in the major weather observing satellites from TAWS to ATAWS. So that's the TIROS operational vertical sounder to the advanced TIROS operational vertical sounder. And that introduces discontinuities in several variables. So the reason for that you can see on the left-hand side, these are vertical weighting functions. So it tells you where the satellite can give you information and how deep that information is. Right, so for TOVs on the left-hand side, you have the stratospheric sounding unit and the microwave sounding unit. These are very coarse in the vertical. And so they don't give you a lot of information about the vertical structure of the atmosphere, which is enormously important for things like storm development or clouds. On the right-hand side, these are weighting functions for the ATOVs set of instruments. And here we can see that there's a lot more vertical information, that resolution is much finer. And so if we look at the time series of this is global mean temperature in a vertical coordinate on the y-axis and in time on the x-axis, you can see that there are discontinuities in the record when the satellite data information that goes into the system is changing, right? So this is something that you need to keep in mind. The third recommendation is to beware of model biases that enter into the reanalysis product itself. So the physical parameterizations are the same as you would find in a climate model, and they can then have these systematic impacts, not just on the forecast variables, which don't have strong data assimilation constraints, but also on the analyzed variables like temperature and humidity. And so an example of that, this is from a paper we had a few years ago. And if you take error 5, it has exactly the same model version as another reanalysis called CERA-20C. It's a coupled reanalysis with atmosphere and ocean information. It's the same version of the model. Error 5 has a finer resolution. The physics that are used in the model are more sophisticated, and it also assimilates a lot more observations. The CERA only assimilates the surface observations like sea level pressure and surface winds. But if we look at the precipitation over the North China Plain, there's a very strong bias in the ECMWF model system, which is eliminated much earlier in CERA-20C than it is in ERA 5. And this is something that we have noticed in other regions as well. And the reason for this is not completely proven, but this is my speculation, and I think it makes sense. The reason for this is that ERA 5 has a very, very high vertical resolution. It has 137 vertical levels. And what that means is that until you get to the very recent years, the information that you get from satellite observations is not sufficient to constrain the vertical structure of the atmosphere, which then relates to things like storm developments and clouds and rainfall, right? And so bigger is not always better in the case of reanalyses. And a final recommendation here is to use more than one reanalysis. So wherever possible, and recognizing that there are constraints on the amount of data that you can use, we recommend users to use more than one reanalysis, right? And here's an example of multiple reanalyses and where you can see that they are different in the variability of the lower tropospheric temperature in the Southern Hemisphere over recent years, right? We try to make this easier to use more than one reanalysis. You can scan the code at the top right. This will take you to the landing page for a reanalysis intercomparison dataset, which uses a relatively coarse grid spacing to provide information from the reanalyses on a common grid and for some commonly used variables, right? And so you can also scan on this page to go to the report that we published in 2022 about reanalyses. And in particular, I direct you, if you are using reanalysis products for any of your work, to go to the chapter 2, which provides information on the models, the data assimilation systems, and really what goes into each of these reanalyses, and provides a lot more detail on what those parts do and what they mean, right? I want to mention that there are lots of different kinds of reanalyses at this point, right? So in recent years, there has been a proliferation of reanalyses focused on air quality, atmospheric chemistry, and composition, reanalyses that deal with coupling between the atmosphere and the ocean. And in the long term, ECMWF and other centers are moving towards reanalyses of the coupled Earth system. But as I close, I want to emphasize that although there are many kinds of reanalyses, there is a common problem that affects all of these different reanalysis products. And the problem is that energy is not conserved, right? So in a reanalysis grid cell, you can take any form of energy from mass or momentum or energy itself, thermal energy. This will change due to the transport, the advection, the physics, any of the parameterizations like convection or radiation, and also the data assimilation. And that third step is what breaks the conservation laws. And so when we want to use a reanalysis, a lot of times for climate records, we really want to be able to close the budgets. And so we can invert what we talked about before. What a reanalysis is not conservative. However, what a reanalysis is complete, or at least as complete as we can get with current climate data records, right? And so one solution, we can use also the type of breakdown that Hassan provided in the previous presentation, right? And so we can think of this in terms of dynamics or advection and the physics and the data assimilation. The current reanalyses, we can actually break this down into an assimilation component, transport component, the physics, and then what actually comes from the data assimilation. And that then gives us a useful residual rather than wrapping a whole bunch of terms in together, which we can use to identify what's actually not resolved by the reanalysis products that we can see, but is resolved by the model that produces those products, right? And so we've constructed similar budgets for temperature, for specific humidity or water vapor, for momentum, for ozone. I'll show you an example of where this can be useful. And so over the southern Amazon, the rainforest begins by increasing its evapotranspiration when you get an increase of sunlight. That then moistens the lower troposphere. And that starts to produce these sort of popcorn clouds, which will mix that water vapor up into the lower troposphere, right? And so in Meritu, so we expect that water vapor from the evapotranspiration to be exported during the dry season. You get a late dry season increase, which then leads to these popcorn clouds and preconditioning, which then produces the conditions for deep convection and monsoon rainfall to ensue, right? But the lower troposphere above the southern Amazon rainforest in Meritu is far too dry. And it could be dry because there's too much moisture export. It could be dry because this shallow convection is not sufficiently effective. It could be dry because the land surface model doesn't produce enough evapotranspiration. But overall, it needs a really huge helping hand to be able to produce the conditions that allow the monsoon onset to take place, right? And so we can use this kind of information that we see here in the lowest panel. We can use this information to try to get it, to try to figure out where, when, and occasionally why reanalyses are different from observations or models or other reanalyses. We can use these to improve our budget allocations, our process understanding, resource attribution for water or heat. We can use them to distinguish real trends from changes in assimilated observations. So you think about those drifts and jumps. In this case, we would expect if it's coming from changes in the observing system, that those drifts and jumps will show up in the increments. We can use them to clarify how data assimilation affects the performance of the reanalysis around extreme events. So we could imagine scenarios in which this helps. You know, the observations allow you to be closer to reality. We could also imagine scenarios in which it hurts because the observations are not co-located with the event, and so they smear out the sharp gradients that are evolving near the event. We can also use them to deepen reanalysis model comparisons, and we can use them to enrich reanalysis-based AI or machine learning tools for forecast and simulation. So smarter loss functions or reinforcement or these kinds of things. I want to close with this, with a few notes on the APARC reanalysis into comparison project. And so we have several community data sets, the one that I mentioned before, and a couple more that we are working on now, a finer resolution common grid dataset for more recent reanalyses, which is 3-dimensional, so latitude, longitude resolve, and these detailed budget diagnostics for analyzed variables like temperature and humidity and momentum, right? We are very actively looking for people who are interested or already using reanalyses to contribute to the intercomparison. We have special issues in atmospheric chemistry and physics and weather and climate dynamics. And the topics that are included within the intercomparison span from monsoons and extreme events through teleconnections, to the stratosphere, atmospheric composition, and air quality, and so on. Right? And so if you're interested, you're very welcome to get in touch. And a couple of closing thoughts, right? So specifically with respect to this workshop here. So because AI forecasting and modeling tools are almost always built on reanalysis products, and in almost all of the cases that I've seen are based on ERA 5, reanalysis evaluation and intercomparison are, in my opinion, increasingly important, even more so than before. And we need to keep in mind the fact that these products are not always convergent. There is a lot of diversity and there are uncertainties that remain in these products that we shouldn't be overlooking when we are using them in these ways. Okay? And I think that by considering energy conversions and transports in carefully designed ways within these algorithms, we may be able to take advantage of this diversity. But one of the things that I've noticed with the AI forecasting tools is a lot of times they will minimize or optimize according to the anomaly correlation coefficient or things like this. But if you actually look at the details of the atmospheric state, it's physically unrealistic. So for example, you can have a warmer subtropics than the tropics. And so your baroclinic instability, your winds or your pressure gradient would be pointing in the opposite direction. But if you look at the mass stream function, it's not closed. Right? And so there are various ways that we can use these closures to help to improve these tools in a way that might, in the long run, make them more suitable for climate type of simulations. Right? And so thank you very much for your attention and for the opportunity to present today. You can get to my website here. I'll mention that we have a number of fellowships for postdocs for PhD students here in China and at Tsinghua University specifically. So if you're interested in these topics, especially water, energy cycles, using reanalyses or modeling tools, you're very welcome to get in touch. Right? Thank you.
Thank you, Jonathan. It's time for questions now. Raise up your hands if you have questions for Jonathan. Yes.
Okay. Hi, Jonathan. You can probably see the question on the chat and Zoom, but I'll ask it out loud as well for the in-person attendees. So the question is for Emmanuel Rangmi. Does any global model provide stratiform rainfall data, reanalysis, which is closest to observation and previous studies available? Can you mention some apart from ERA 5?
So all of the current reanalyses do provide stratiform rainfall. Right? So there will be a decomposition between the convective rain and the stratiform rain. You need to be aware, this is something that I didn't mention in this presentation, but you can find it in the report, that separation is not always the same. And so that depends very much on the physical parameterizations that are used in the model, how exactly that discretization is. Which one is closest to observations? I would say that's going to be highly regional. Right? So it depends on what constraints you have and how the physical parameterizations behave in different environments.
Okay, we have a question here.
Good morning, sir. Thank you for your talk. So I have a question related to the reanalysis. And when we say that energy is not conserved, can you explain more with this concept?
So basically what happens is that if you only had the model, then energy would be conserved. And if everything exactly matched reality, then energy would, of course, be conserved. But because you have this data assimilation component, what happens, so you could think of this in terms of the example that I showed, right? So in Meru, the lower troposphere is far too dry. And so what happens is the data assimilation is always adding water vapor there. It's adding water vapor there because the observations say there should be more water vapor there. But what that does is it feeds stronger and stronger precipitation. And so you'll see that almost all of the reanalyses will overestimate precipitation. And that's because their atmospheres are too dry in the model, and the data assimilation constantly adds water vapor. So you can do an experiment. So if you think about the total north-south energy transport, you can calculate this. And if you do this for a reanalysis, what you'll see, you start from the South Pole and you integrate all the way to the North Pole. And what you have is multiple petawatts of energy streaming out of the North Pole into space if you don't correct for this lack of energy conservation. And so the imbalance is very, very large in a global sense. And it's going to be regionally very different, situationally very different. And so as a result, there's no general rules that we can use to kind of say, how can we actually close that in the end? And so that's what I mean by the lack of closure, is that if your reanalysis is too cold here, then the assimilation will increase the temperatures, not for any physical reason, but because there's a mismatch between the model and the observations. And that then adds heat, which has no physical source. Right? Thank you for the question.
We have more questions? Okay. Jonathan, wait, there's still more questions for you.
Okay, so thank you. When you use the ERA5, sometimes the free data is like it's not the recent year. So when you saw your data is like 2021, and what can we do if you need to use the recent data like real life and to evaluate the model and to find the good conclusion and analysis for policymakers, something like that?
Yeah. So it's a good question. ERA5, I think they do a relatively good job of making the most recent reanalysis available. There's what's called the near real-time product. I think it's called ERA5T. And if you are looking to study an event that has just happened, you can look at the website for ERA5T and you can get the most recent data. So otherwise you'll need to wait multiple months. The potential issue with that is it's not final, right? So they will still make some corrections. They will identify some observations that had some issues, and the final ERA5 product will be something a little bit different, right? I think this is something that ECMWF does pretty well. And I think most of the current reanalyses will have something similar. It's not always super easy to find, but if you are having trouble identifying where to get it or how to get it, you can always get in touch with us in the reanalysis into comparison. We have a lot of resources on this.
Any more questions for Jonathan in person?
Yes, here is Shaukat Ali. It was nice presentation. I'm curious about that. Currently, I'm in Beijing, and I'm working with Chinese Academy of Sciences. So there is any chance for the potential collaboration with you in Tsinghua University related to artificial intelligence used for the climate models or for the data analysis?
So our group doesn't do very much with AI tools, although we're interested in how what we do with these budgets and various energy cycle diagnostics could be useful for that. And so I would very much welcome collaborations along these lines.
Okay, thank you very much, Jonathan, and everyone. So if you still have more questions for Jonathan, you can contact him by his email. Now we have to go for break. Thank you very much.
Thank you.
So just before we go to coffee break, I mean, yesterday, each one of us, I don't exclude myself, we used the bottles and we did not bring them back and we left them here. So please take care of that. Whoever used his bottle, you can just place it on the stuff that it will reduce at least amount of work for the people outside. And then, yeah, I think it's, yeah, coffee break time. So enjoy and keep. Jonathan, thank you. So before that, we can also thank all the speakers that have been online today for the morning session. Just an upload for them. Yeah. Thank you for your time. I think it's for you. It's already evening. Yeah. So then, yeah, let's catch up in the next sections. Yeah. So enjoy your coffee break. With off already. Jonathan, are you online? It was already off.
Yeah, I'm here.
Yeah. Do you hear us?
Oh,
I
you,
mean,
you need me to unshare, right? That's again these two different devices. I
So
forget.
thank you for your time, and we also thank all the speakers online this morning. I mean, the mic was off. So let's catch up in maybe yeah, less than 30 minutes for the coffee break. Yep.
J'ai pas reçu l'email.
Sorry?
Je pense que the email,
Oui.
I think it's wrong. Et je pense que j'ai pas reçu l'email. Je
Ah,
pense que oui.
Parce que il y a un des emails qui n'était pas bien écrit là, que j'ai pas compris. Ara?
Arabe et Mansour.
Et ça c'est quoi exactement? Le T-R-A-O.
T-S-O-A.
T-S-O-A.
Ah. Ok, c'est comme ça.
C'est parce que là, je ne savais pas c'était quoi là exactement.
Ok.
D'accord, ok, je vais vous faire suivre.
Pas écrit le mieux.
Toi, tu es dans le truc déjà normalement?
Ok, d'accord.
Tu l'as pas reçu? Oui? Tu l'as pas reçu hier soir un email qui vient de moi?
Oui, bien sûr.
Oui, donc c'est bon.
Ok.
Ça, c'était juste hier. Tu avais écrit ici sur ça hier?
Non.
Il fallait émarger ici.
Bon, j'ai mis mon nom.
Tu as mis ton nom?
Ouais.
Non, c'est bon. Le reste, si tu avais mis ton nom hier, c'était juste pour savoir les gens qui étaient là. Oui, c'est bon. Non, c'est bon. Nous, on doit travailler. Mais d'abord, il faut aller voir le capital.
Non, sérieux, c'est beaucoup.
Hein?
C'est beaucoup de travail.
C'est beaucoup de travail?
Ah ouais.
Tu n'es pas inscrit? Là, je dis ton nom. Oui, on doit voir deux choses là.
Il faut qu'on accélère.
Oui, j'ai déjà, peut-être, on peut prendre un café après, s'il vous plaît.
Oui, à la pause de 13 heures, ça dépend.
Non, mais juste on peut le faire maintenant. De toute façon, maintenant, je laisse tout à les autres là. Je ne fais plus le compte. Ça marche. Coming from Dakar. No, it was really not. Right. Oh, I was thinking you have nothing, but it looks like you have already. I was thinking you have nothing. Yeah. If you are Thai, you can give this young man share a little bit if you want.
Yeah.
Or you can share what as you want.
No, it's also good, like they had experience, so I'll call him.
Unless that you have some.
It's good if you can also have some experience.
But if you don't, it doesn't matter. If you don't have anything,
No, it doesn't matter. It's nothing.
Just please do it if you don't have something. But you have, go ahead. Go for it, please. Go ahead.
Oh, he didn't come because I think problem was his flight.
Do you know if
He's
he's
used about three times the price, even though I talked about it covered it.
do you know if he's online?
I don't know. Let me send him an email. My Zoom also is gone.
Okay. Maria, is your Zoom?
I will ask.
Okay.
I
Yeah, you can also chat to me.
Who's supposed to talk now?
Is one. Is robot in jacket?
Oh. Oh, wait.
Am I know?
After. Yeah, Robert Miyake. Let me just call him and then see if he's online. Otherwise, we have to skip this stuff and then we aren't the stuff.
Okay, we can.
Wait. I think he told me finally how only checking me.
Oh.
But if it's like 30 minutes later, then I can call. Like it's like alert me. You can take the next one and then we can push the top away.
Okay, so the next person is Kela.
Yeah, okay. Yeah, sorry about that. Now it's already uploaded. I just asked her.
Okay. Yeah, Michaela.
She's quite busy also.
Is about ozone impact.
Hello. Are you talking about me more? I was sorry. I didn't understand that the agenda did change. I expected that Professor Mbake was talking now.
Yeah, I mean, he is not online. We try to reach him, but he's not responding.
Yeah.
So
So should I give
maybe
mine first?
yeah, maybe you can just go on and then we can shift everything. In the meantime, I will try to catch him.
Yeah.
On WhatsApp. Okay,
Yeah.
thank you.
Should I do that?
Yes.
Yes.
Okay, I hope that he will give a good introduction for me. So let's see. I try to share my screen.
Yes, so our next speaker is Professor Michela, and she'll be talking on ozone's impact on the environment in context of climate change.
Yeah, can you actually see my full screen?
Yes.
Or is it just a presentation, not my laptop?
No, we can see your presentation. It's very fine.
Oh, now I lost my, sorry, I'm coming. Okay. I think, so sorry, yes. Hope everybody's back from the break. Thank you very much for inviting me here to give a talk. And hello, everybody in the room and also outside. For those who have not joined, for those who have joined today only, I'm Michaela Hecklin, and I'm a director of the Institute of Climate and Energy Systems at the Forschungszentrum Jülich in Germany. So as I was already introduced, I will talk about the ozone impacts and on the environment in the context of climate change today. Okay, I thought Professor Mbiaka would introduce chemistry climate modeling to you. So I go back to what you learned this morning from Professor Hirsentimaki, and who has introduced you this morning to the Earth system modeling and the different Earth system components that make up the climate system. In this lecture here, we will have a closer look at the atmosphere. So this is one part of the Earth system, and more specifically, the stratosphere, which plays a significant role in modulating climate variability. But more importantly, it also hosts the stratospheric ozone layer. As you can see on this slide here, the stratospheric ozone layer is considered one of the planetary boundaries. These planetary boundaries are a concept that defines safe operating zones for humanity with respect to different Earth system processes whose disruption could destabilize the planet's environmental conditions and have bad impacts on humanity. They include. Oh, now I'll try to find. Can I do a remote control? No. How you call it?
What would you like to do?
A pointer. No, I can't do a pointer. Sorry. Now I did something very wrong. Sorry. I have to close that again. Yeah, I think I can't. Can you see my mouse?
Yes, we can see your mouse.
Oh, very good. That is wonderful. So, okay. So these are the planetary boundaries that define these safe operating zones for humanity. And they are not only stratospheric ozone depletion, as I just said, but also climate change, biosphere integrity, land system change, freshwater change, biogeochemical flows, ocean acidification, and atmospheric aerosol loading. As you can see from these colors, as soon as one of these planetary boundaries moves into a red zone, the safe zones for humanity are breached. Stratospheric ozone depletion, on the other hand, is currently considered safe. But if you talk to stratospheric scientists like me, then maybe we should still keep an eye on it because there is a new threat on the horizon that I will, in the end of this lecture, hopefully also have introduced to you. Okay, what are we talking about? We're talking now about the chemical composition of the Earth system, and the chemical composition that Professor Mbiaka would have introduced to you. He would have told you that it is changes in this chemical composition of the atmosphere that actually is driving climate change. So the increases of carbon dioxide, of other greenhouse gases like N2O, methane, and ozone depleting substances, they all create climate change. But then also the air pollutants that are emitted when you burn fossil fuels, then you are actually also getting a secondary pollutant that is called ozone, and that one is also causing climate change. So we have to have a look at the atmospheric composition. And ozone is one of these constituents, and the primary effect of ozone, or the main area where the ozone resides is in the stratosphere. In the stratosphere. This is around, let's say, 10 to 50 kilometers. So in here, in this layer above our heads, resides this ozone layer. And you can see it in this profile where you see the ozone abundance on the x-axis and altitude in the y-axis. So this is an ozone profile that would have been taken by a balloon ozone sounding. And you can see that in the stratosphere, there is the ozone layer indicated, and that is about 90% of the total ozone in the atmosphere that you can find up here. And in this layer, that ozone is considered to be a good ozone because it protects the Earth from harmful ultraviolet radiation. And this ultraviolet radiation, it's made out of UVC, that is really hard radiation, but 99% of that radiation is absorbed within the ozone layer and above. Then UVB, this is about 90% of that one is absorbed by the ozone layer. The rest will be coming down onto the Earth's surface. And UVA is also absorbed by ozone, but only about 50% of it. The rest is also received by the Earth's surface. So why is UV not so good for humans? So it can cause, if you have too much of it, it can cause skin cancer. We need, though, a little bit of UV because it also helps to create vitamin D in the body. So it is not only bad, but you need the right balance. You need a little bit of it, but not too much. Then you have the ozone at the Earth's surface. And here you have also ozone increases. But this ozone increases, as I said in my introduction briefly, comes from air pollution. So ozone is a secondary pollutant that comes from these fossil fuel burning that is doing air pollution that you sometimes or that you might feel in big cities where you live. So ozone at the surface is actually harmful to the ecosystem and human health, and that's why it is considered the bad ozone. So we go now back up into the stratosphere because my lecture is mostly on the stratosphere. And I would like to show you now how the ozone layer is distributed, or the ozone in the atmosphere as a total is distributed, and how it interacts with climate change or climate variability. So what you can see on the left-hand side is a zonal mean cross-section from a satellite limb sounder that is called OSIRIS. And you can see that the red colors indicate large ozone concentrations, while the blue colors is little. And that is corresponding to this vertical profile that I showed you from before. But you can see that there is really this layer up here of high ozone concentrations, and that's again this ozone layer. You can see indicated with these profiles, these are waves that propagate up from the troposphere that break in the atmosphere and deposit momentum, or in lay terms, energy. And that one drives the stratospheric general circulation and moves the ozone from its production region in the tropics, where most of the sun comes in, to the extratropics and to higher latitudes. And that's why you see, especially in winter, you see these high concentrations of ozone. You can see this concept of the planetary wave-driven atmospheric circulation on the right-hand side. This is a famous picture from Alan Plum. And you can see here the Hadley cell indicated in this equatorial circle here. And then you have different waves, planetary waves that are breaking in the middle stratosphere to drive the deep branch of the stratospheric circulation. And then you have synoptic scale waves that are generated by weather systems that break in the subtropics and create this this shallower branch of the Brouwer-Dobson circulation or stratospheric circulation. And all of these waves that are breaking and are driving this transport are important for the distribution and redistribution of ozone. It has a variability in it, a seasonal variability in it. In the winter hemisphere, you have always more ozone. In the summer hemisphere, you have almost less ozone because there is less wave driving. All right. So then the next problem that or environmental problem that we discovered in the 1980s was the ozone hole. Now, if I would be in class, I would like to see a hands up. Who of you would still know what the ozone hole is? Did you actually learn that? Because you're in a generation that maybe that problem is a long way ago gone, and you might not never have heard of it. Does anybody has heard of it? Oh, I see no single hand. So, all right. So I'll talk you through this then in this case now. Thank you, Maria. So there, on the left-hand side, you see ground-based measurements that were made by people sitting in the Antarctica in the dark winter, and through many years, since the 1950s, and through over 30 decades, they have been measuring total column ozone from below, and they have measured the amount of ozone that was in the atmosphere. And so years along, there was some variability in it, but then they didn't really, well, it was maybe boring to sit there in the dark, but the people liked to be in the Antarctica, so they kept measuring, and all of a sudden, they found that the ozone concentrations, they dropped from year to year very severely. And in 1985, this paper by Farman et al. Came out in Nature to show that there is this huge ozone decline, and it was an inverse relationship to substances that are called chlorofluorocarbons, and they are depicted on an inverse scale here by these dots and points on here. And you can see there is an inverse relationship, and by these measurements, basically, the theory from Rowland and Molina was also Molina was confirmed that CFCs can lead to this environmental problem and deplete stratospheric ozone. These data were not that, so there was a big concern about how big this ozone depletion would have been around the world. But it was only when NASA went back into their satellite measurements that could be revealed. And you can see here up here some globes with total column ozone measurements from the 1980s, across the 1980s. And you can see that over time, there is this blue bubble coming out that is getting more and more severe. And that basically shows you what is now dubbed the ozone hole. So that is the emergence of the ozone hole as they discovered in the southern hemisphere in the 1980s. Scientists had warned of the ozone hole, ozone depletion that it could happen, but they were never expecting that it was leading to such a big hole over the Antarctica. And a lot of science had to be done to help explain where it is coming from. And just to give you a small reference here, 1% less ozone leads to about 1 to 2% more UV on the ground. And depending on where you live, how much ozone, how much more UV you get, how much exposure you have, if you work on the fields or if you are high up on the mountains, you have a lot of UV coming down, then you can have a similar amount, like 1 to 2%, maybe even 3% more increases in cancer or in skin cancer occurrences. So then there was, in 1987, there was an international treaty that was called the Montreal Protocol, which the world's nations have come together to phase out these chlorofluorocarbons, these CFCs, that are responsible for the ozone depletion and the ozone hole. And the Montreal Protocol is now considered the most successful environmental agreement in history. I'm not going much more into that, but I would like to make a link to machine learning and AI now, because what we learn even already from this very early example was that you have to be very careful with data evaluation. So the ozone hole was really a big discovery, because that was really a big environmental problem that was predicted. People didn't act, but then only when we had this really impressive information from research, from satellite and ground-based observations, only then people acted. And so that was a really big discovery. But it was actually the Farman et al. Paper that was from a British research crew that was publishing that. And it was not the Americans, and there was always a little bit of a competition between the Americans and the Brits in terms of science. So a very human aspect of science as well. But then when NASA went back and they said, oh, in principle, we should have seen that in our data, they had to go back and look into the satellite data again, because they had actually thrown out these very low ozone data points from their retrievals, from their satellite measurements by an algorithm. So they used this algorithm to screen for outliers, and they kicked these outliers out, and they were missing the ozone hole. So that is not only bad luck, but that was really a big story for NASA as well in the world, because, and also now a lesson for you, hopefully, that if you automatize something, you always have to keep an eye on reality. All right, so now I'm going a little bit more into complexer ways of looking at the ozone layer, and how we actually, now that we have dealt with the problem, how we can start looking whether the ozone layer is starting to recover again. And one of these tools that we have are chemistry climate models. And these are similar to these Earth system models that you have heard of from this morning from Hyacinth. And but what they also include is specifically chemistry, and specifically stratospheric chemistry that can simulate this ozone depletion going on. And then I also go back to Jonathan's talk about the reanalyses. What we have done in this model simulation here, we have actually married an Earth system model with a reanalysis data set. That is, we have nudged the dynamics from the chemistry climate model that we used, from this Earth system model that we used. We have nudged that to observed net meteorology, that the transport in the model is like on a monthly scale, exactly the one that you would have observed. And now comes the nice thing about it. We have been able to show that actually you can even resolve all the transport in the stratosphere very well, and how this transport affects ozone. And we do that through this indirect way of looking at it. So what you can see here in the uppermost panel, this is total column of ozone, and the blue line, sorry, my eyes are not good enough. The blue line, no, the orange line, no, sorry. The screen has changed the colors. This is bizarre. Anyway, sorry. The orange line was the observations. Then we have a black line that will be lying under here, and you can see how it follows the observations. And this Earth system simulation, the black line, has actually all the ozone depleting substances in it. So it can follow the atmospheric concentration fluctuations in ozone, in total column ozone, very well. All the ups and downs are reflected in that. If you take out these ozone depleting substances and you have a constant value in it at 1960s levels, when they were not yet in the atmosphere, then you can see how the ozone would have stayed at about the same level across these decades from 1960 to 2010. The difference of it is actually ozone depletion. If you just look at the stratospheric column, you can also see that the model that is driven with these reanalyses, that was the ERA interim reanalyses back then when we published this paper, you can see that all the vehicles are very well resolved as well by stratospheric limb sounder observations that are depicted here in different colors. And as I just said already, if you take now the differences between the blue and the black model simulation, you can get at the amount of ozone depletion that you had in the atmosphere. And then you can see that in the 1980s, or even before the 1980s, you had some ozone depletion going on. People didn't realize it yet. In the 1980s, when the ozone layer was found, you can see that the ozone decline was depletion was much stronger. And then after the Montreal Protocol had been put in place, the ozone depletion has halted and even reversed by a bit. So by 2010, back then, 10% reversal in ODS-induced ozone loss could be identified by this methodology. And that is attributable to the success of the Montreal Protocol, which is a political instrument to ban these ozone-depleting substances, these CFCs. And you can also directly measure these CFCs, and this is a surrogate of these CFCs. This is called hydrogen chloride that is measured in the stratosphere. And you can see how in the 1990s, because of its longer lifetime, it has increased and has peaked around 2000, and since then is in decline. On the right-hand side, you see all the ingredients that form these ozone-depleting substances. So, for example, there are also some natural ones like methyl chloride, but then the main human anthropogenic CFCs are CFC12 and CFC11. They make up about they make up a large part of the total amount of ozone depleting substances. And you can see the difference between the amounts of them in the atmosphere in 1993, and in 2012. This is before or at the peak of the ozone depletion, and that is after, like 20 years after the Montreal Protocol had been put in place. And you can see in between these 10 years, there was a decrease of these ozone depleting substances in the atmosphere by 10%. So this is equivalent to what I showed you before. This is equivalent to the ozone increases that we saw again, or the reduction in the ozone depletion that we have seen in the slide before. On the right-hand side, on the left-hand side, you see the chlorine source gases, and on the right-hand side, you see the bromine source gases. Both of those are atoms that come out of these ozone depleting substances that are in the end responsible for the ozone depletion in the atmosphere. All right, and now we go on. We look now into the future, and while ozone recovery is expected in the future, I will now show you that due to increasing greenhouse gases, our chemistry climate models project a strengthening of these general stratospheric circulation, which we call the Brewer-Dobson circulation, and that this one affects the distribution of stratospheric ozone. So on the left-hand side, you see a surrogate of, or you see, not a surrogate, but you see the W star, which is a measure for the Brewer-Dobson circulation strength. And where you see red colors, you can see that means an increasing upwelling, while the blue colors indicate an increasing downwelling. So you have an increase in the stratospheric circulation. And then on the right-hand side, you see how that affects ozone. You can see in the contours how ozone is distributed in the past. And then in the color shading, you can see how ozone then changes. And you can see that in the tropics, you can see that due to this enhanced transport out of the tropics into the extratropics, that you take away ozone from the tropics and you transport it into the extratropics. So while overall in the upper stratosphere, you have ozone recovery going on in the across the tropical region, there is quite a strong decline in ozone expected from our models. What does that have? It has an impact on UV. Well, I should first say the amount of how this ozone changes in the tropics is very much depending on the future climate emission scenarios that are driving the climate simulations for IPCC and the CIMIP world. And you can see this was in the earlier round 2021. The emission pathways have been named representative concentration pathways. So these are different emission scenarios that the world would follow, depending on whether we would have a low emission scenarios in greenhouse gases, which is RCP 2.6, or whether there is this red one, which means we emit a lot of greenhouse gases in the future. So if you do that with these different scenarios, then you can see in the tropics that, again, if you look at the total column change in ozone, so this is an anomaly in the ozone layer. Here we have some observations over the recent past. In the tropics, it was not as clear as otherwise that ozone depletion had been happening due to ozone depleting substances. But if you have a close look, you can even see that even in the tropics, there was some decline. But then if you look now into the future, and in this timeline of tropical ozone, you can see that in some scenarios, in the middle scenarios and low scenarios of climate change, that ozone never recovers to 1980 background. In RCP 8.5, it is actually recovering, but that is due to heavy ozone pollution in the troposphere. So both of all of these scenarios are not good news, especially these middle past scenarios. They lead to these ozone decreases that then translate into UV increases across the tropics into the future. So what you can see here is the 2,100 expected UV changes with respect to 1980 levels. No, sorry, 1960 levels. And you can see that in the tropics, we expect between around 3 to 5% more UV, according to that one model, in the tropics. While in the extratropics, we are actually having about 10% less, less UV than normal, which is actually also a bad environmental impact, because especially at the higher latitudes, people have a lot of deficiencies in getting enough UV, so which is not good for health either. So this imbalance in the stratospheric ozone layer in the future might have bad health effects. You can see it on the right-hand side. This is just a zonal mean cross-section of how the stratospheric column changes are related to the ultraviolet index here in red. Okay. Another aspect of these changes in the stratosphere that affect the ozone layer is also how much ozone that comes from the stratosphere into the troposphere, where it might affect tropospheric ozone pollution. And if you plot this, if you calculate this amount of ozone in the stratosphere that comes through a certain level, usually we take the tropopause level that is around 12 kilometers height or 100 hectopascal. You can do whatever you want. In the end, it's about the same amount that comes down. If you use this metric and you calculate it on an average global mean level in the Northern Hemisphere, you can see how this stratosphere, troposphere ozone is actually increasing over time between 1960s and 2100 by 2.6% a decade. In the southern hemisphere, the story is a little bit different because ozone depletion is actually the stratospheric ozone depletion that is caused by the ozone hole and so on. There is a negative imprint first, so you have a decrease, and as soon as the ozone layer is recovering, you also have a slight increase, but a less strong increase in the southern hemisphere, so about 0.8% per decade. Yeah, so this is to be considered. So what is coming down from the stratosphere into the troposphere, and why do we care? In the troposphere, what we have, what Professor Mbiaka would have told you, there is the problem of ozone pollution. So air pollution, part of air pollution is ozone pollution. And what you can see here, so this is now also from a chemistry climate model, or from two different, from EMAC and CMAM. And you can see here the trends between the 2000s, so the last decade, so 2000 to 2010, to the 1980s. And this is a PhD student of mine who had done these figures. And he found that this is not only his research, but a lot of people have shown that there is a general increase in ozone that is largest in the northern hemisphere, around 4 to 8 ppb, and in the southern hemisphere subtropics, 2 to 6 ppb per over this time period, which is quite a large effect when you come down into the troposphere. So these are showing you at different levels. You have here at 350 hectopascal, at 500 hectopascal, which is about equivalent to 5 kilometers. And then this one here is at the surface. And you can also see that around Asia, that there, because of the really high air pollution that they have, a lot of fossil fuel burning, a lot of emissions, that they have the largest increases in ozone pollution at the surface. The second model shows similar pattern, but in the southern hemisphere, high latitudes, it shows decreases that are likely connected to the stratospheric ozone depletion and that stratosphere-troposphere exchange that I just told you about. He then used a tagged tracer, so you can, in your models, you can follow your molecules, your trace gases, by tagging them. You give them a label and you see whether an ozone is coming from the stratosphere, and then you follow it where it goes into the atmosphere. And that was my student has done here too. And he was able to show that a lot of the trend, so about 25 to 30% at the surface and 50 to 80% in the upper troposphere, in the change that we just observed in total tropospheric ozone at these different layers that I showed you before, is actually due to an increase from the stratosphere. So you have to be considering this increase as well. All right. So I move on, and this is a different aspect, which also Professor Mbiaka would have told you, that ozone is also a greenhouse gas. And now you can look at how these changes, these changes due to due to ozone depleting substances have affected the radiative forcing of climate. Radiative forcing of climate is a measure. It is measured in watt per square meters, and there's equivalent numbers for the CO2 forcing, the CO2 radiative forcing, and so on. So you can see here that ozone also has such a radiative forcing, and what is depicted on the left-hand side is the stratospheric radiative forcing due to the changes from the 1960s to, no, that is now going back to 1850s to the 2000s. First, the lower part is to the radiative forcing between the 1970s and 1850, and the upper panel is between the 2000s and 1850. And in the 1970s, there was no ozone depletion yet. You can see that due to increasing methane, there was an increase also in the stratosphere. We had some increases in stratospheric ozone. So this led overall to a positive stratospheric radiative forcing. And in the when you go now to the 2000s, you can see that the stratospheric forcing is actually negative in the southern hemisphere due to ozone depletion. So that has caused a small contribution to a cooling of climate during the time of ozone depletion. But it's so small, these changes were not able to explain climate change, or also not able to counteract climate change. Whereas on the right-hand side, you can see now the radiative forcing is much longer now. You can see much larger now, and it can reach up to about 0.9 watts per square meter, depending on the region where the highest pollution is actually observed. So due to tropospheric ozone changes, which have increased over time, we do have this positive radiative forcing and this contribution of ozone and therefore air pollution to climate change. Okay, and then how much time do I still have? Can anybody tell me?
Yeah, maybe if you can round up in a few minutes so that we see if we can take a few questions for you.
Yeah. Okay. So the last part that I would like to just introduce is that ozone is actually not only is not only driving changes in the mean radiative forcing of climate change, but it also drives local changes in the dynamics of the atmosphere. And that's what you can see in here. That is now again chemistry. These are Earth system simulations with prescribed ozone changes between 2014 and 1950s over the past, and you can see that these differences in or ozone changes, they drive distinct responses in the zonal mean winds of the atmosphere. So you're looking here at a cross section in the southern hemisphere between 90 degrees south and 10 degrees south. So only the southern hemisphere considered. And you can see here in the contours again, the mean distribution of zonal winds, and in red, the changes due to over this time period. Now you can look at simulations that have only stratospheric ozone changes only, and you can identify that stratospheric ozone changes led to a strengthening of the southern hemisphere polar vortex. And then if you just look at the simulation where tropospheric ozone changes are simulated, then you can see that these strengthen the upward and equator shift of a subtropical jet. So these are two distinct changes that these ozone distributions have been leading to. And they act down to the surface. And it has been observed that the stratospheric ozone depletion over the past has been actually affecting surface climate, especially in summer in summer in the southern hemisphere. So this is also one thing to keep in mind. Then you have ozone versus other greenhouse gas driven the ozone versus other greenhouse gas driven changes in ocean heat content, and you can see that the ozone, both the ozone, the changes in the stratosphere, in the troposphere, they have led to an increase in the ocean heat uptake, as have done other greenhouse gases like CO2 and N2O or methane. And you can split that up now into the tropospheric and the stratospheric part, and they both led to an increase in ocean heat uptake. All right, I come to my summary, and I'd like to highlight again that stratospheric ozone hole was a really wake-up call for the global community. It revealed how human technology, once seen only as a progress, could unintentionally damage the planet's protective ozone layer. And the success of the Montreal Protocol to ban the production and use of these CFCs should serve as an encouraging example that the world's nation can actually deal with a severe global environmental problem, such as also climate change. But climate change is a wicked problem. I do acknowledge that. It's of much higher complexity than what was driving and was causing the ozone layer. But we do understand climate change, and we do have solutions to limit its destructive impacts. So climate change as a whole is a new threat to the stratospheric ozone layer. We have to keep an eye on it. I have told you that the strengthened broad adoption circulation from increased greenhouse gases can decrease total column ozone and increase UV across the tropics. And this is happening during all seasons and for all climate change scenarios that we currently are looking at. But we still need to make observations because we do not really know whether our chemistry climate models are correct in doing these predictions. And then I want to make a point again back to machine learning and AI. It can be a promising tool to simplify the evaluation of atmospheric observations, but it should definitely not replace physical knowledge. And you should always think of your tools and always think of how the atmosphere or how the climate system is physically functioning. Because you could miss new features that were not in the data that are going into your training pool of your machine learning methodology. And you should always check also your results on using common sense and your physical knowledge to check what you're getting out of your machine learning applications. With that, I thank you for this, for your attention.
Okay, so thank you, Michaela. It's time for questions now. Yes, we have a question.
Thank you, Professor, for your nice talk. So my question is about the releasing of CFC in the stratosphere. So how this concentration will affect the ozone layer. And I also see in your last slide, in your summary, so you said from an increased greenhouse effect in the stratosphere will affect the ozone layer. So I would like to know how this can happen. Thank you.
Yeah, so these CFCs, so they were used in refrigerators. They were used in spray cans in the 1980s before they were banned, and in many other applications as well. And they were really considered long-lived. So they were emitted at the ground, on the Earth's surface. And because they were so long-lived, they were able to travel and distribute across the atmosphere. And they came them into the atmosphere, also into the upper layers, into the stratosphere. So through the general atmospheric circulation, these CFCs were transported up into the stratosphere. In the stratosphere, you have much higher and much stronger UV radiation, much harder UV radiation. And this hard radiation is able to photolyze, we call it, these long-lived substances. And in this process of photolysis, it is releasing chemical atoms that are called chlorine and bromine, and they then lead in catalytic reaction cycles. They can attack a lot of ozone molecules, which are made out of 3 oxygen atoms, and they have been able to attack that and deplete this ozone. So it is this process of transport from the surface up in the stratosphere that the stratospheric ozone layer have been in the past led to the depletion. But these substances are now banned, and we don't emit them anymore. Well, we hope. There was a case that in China, there was a new production in the 2010s, but we were able to identify that early enough, and the Chinese government was very fast after they realized that this happened, was cranking down on the production of these CFCs again. So in principle, we should not produce these substances anymore. So we should see now that the ozone depletion is not a continuing issue, but the chemical ozone depletion should go away into the future. So this is the first part. Then the second part is that because we have CO2 increasing in the atmosphere, which is another inert greenhouse gas, you'll get warming of the troposphere, and that is changing the dynamics in the atmosphere. It changes the wave driving of the general circulation in the stratosphere, because it creates, let's say, more waves that propagate into the stratosphere, or they propagate differently, and then they affect the transport, and through this transport, the ozone layer is now redistributed. So this is a transport, a dynamical, a physical effect, while the other one was a chemical effect. Does that make this the difference a bit clearer now?
Yeah, you can just ask your question. Do we have another question? Okay.
Okay, thank you, Professor, for your informative presentation. You were explaining that we should not replace physical models by ML models. I was asking, like, there is also models that try to combine ML models and then bring the physics to it, the physics informed neural networks, where they try to add a loss function that's to the normal loss function in ML that take into account the physics or some constraints. I would like to ask if the study of ozone impacts can also follow the same process. Thank you.
Yes, thank you for your question. And I have to make a clarification here. I didn't mean one should not use machine learning tools as replacement for physical models. We should never replace machine learning for physical knowledge, which is slightly different, right? You still need to know what you are looking at. This knowledge in your what you are learning from observations, from models, like what the equations that are behind it. We should always keep them in mind, so that we can test when we apply a machine learning methodology, and when we make a machine learning model, when we generate one, that you can validate whether the answer it gives you to a certain problem is reasonable or not, is consistent with our physical knowledge. That's what I meant. And you're totally right. Like this is, I think, for the future, it is the most powerful thing to do. We can use machine learning to simplify our models. We can look at the main drivers. Like machine learning is really nice to look at what are the main drivers of a physical variable or so, and then we can learn through that, and we can go back and improve our physical models with this knowledge as well. Or we can just simply simplify for weather predictions, so that more of us can actually make weather predictions and don't need to run fancy and expensive models that use a lot of energy. So yes, you're totally correct. Like machine learning in combination with our physical models is a fantastic combination, and a very promising combination. But still, it's a tool, and you have to be careful of how to use it. You should never blindly believe observations. You should never blindly believe models. Always check whether the physical thinking is correct, that is behind it.
Okay. Yes, so another question here.
Yep.
Thank you, Madam. Sorry, I need to understand well the case of the hole in the ozone layer. If you know that this one is caused by the CFC gas, we need to understand what the measure we can take to address this one. Like we know, for example, the aerosol and the fridge is the reason to produce this kind of gases. How can we achieve this one in the real world?
Yes, so this was a huge process. When the scientists found out that there is an ozone layer, and we knew the theory behind it, that it is actually these chlorofluorocarbons that are widely used in different applications, one was able to say, okay, there was a second technical panel, it was called, that was together with industry searching for solutions, and that has led to replacements of all these harmful substances, and we do have now other technologies. So our fridges, they should have now all cooling gases in them that are not harmful anymore to the stratospheric ozone layer. So all these substances that have been in the past emitted, they should have been removed, or they should not be produced anymore. So this problem in principle is solved through this international treaty, the Montreal Protocol. Does that answer your question?
Yes, I believe so. And then we'll go ahead and take an online question now. Michaela, I encourage you to take a look at the chat, because it appears that the question I'm going to be reading for everyone in the room is from someone who visited your lab recently to work, but they are interested in the topic on checking global warming with geoengineering methods like stratospheric aerosol injection. And so they're thinking about how things like sulfates, aluminum oxide are injected into the atmosphere to reflect some of the incoming radiation. And that means the tropics will be the most effective area for this injection. I'm thinking because of how it spreads out in the stratosphere. Will this by any way influence ozone distribution, as ozone production is within the tropical region and transported polewards? That is the question.
Yes. So this is a really good question, and it has a lot of relevance nowadays, because as we see that climate change is happening and that the world is not acting fast enough in combating climate change, the idea came up that we could simulate like what we call like a big volcanic eruption that is putting a lot of aerosol into the atmosphere and into the stratosphere. Because we have observed when that happens from a natural point of view, when a volcano goes off and happens to put all the sulfur into the stratosphere, it can lead to a cooling of the Earth's surface. So now people have the idea to make that from a technological way, sorry. And to basically put with aircraft, balloons or whatever, aerosol particles or aluminum particles, a lot of, different kinds of particles that reflect radiation, solar radiation back to space, so that it doesn't reach the Earth's surface, so that it cools. There's a lot of problems with that are associated with it, that can not only cause the stratospheric ozone layer to be damaged again in a more severe way, which we need to keep an eye on as well, if people all of a sudden have this idea to come up with these geoengineering approaches. But it also because what I showed you, the stratospheric circulation and the interaction with climate could affect how the dynamics in the troposphere are changed. And that could lead to precipitation changes in different regions of the world that will be another severe impact. Maybe it would take away the global mean temperature rise, so it will be cooling a little bit, but it could lead to other severe effects. And this is a huge research topic now, because there are more and more people talking about doing it. And I want to make a strong statement here that we really need, before we do something like that, we need to research more the risks of what could happen when we do such technical fixes to climate change.
Okay, one more question.
Okay, thank you for this amazing presentation. My question, it is more related to machine learning. We know that sometimes to train our model, we need all data in climate, Like we need previous data. So we notice that the humans beings have, for example, an impact to the ozone hole. So when we train, for example, our model with data, how can we manage, or how can we handle, for example, the climate change, the impact of climate change into our data? Because if I have, for example, the data of this year, for the next year, for example, we can have the impact of the climate change to that data. I don't know how the machine learning can handle it. Thank you.
Oh, this is a very good question, and I do think I might not be able to answer that one too well. And I would maybe refer to the machine learning. I'm not really a machine learning person or expert here. I have to admit that. So what I understand is if you have in your machine learning tool, if you prescribe or if you use the ML model, also you give it observations to learn from these observations. So you would need a long enough time series, and you might also take an index or a surrogate for the stratospheric ozone, for example, that might be giving you some variability and might give you some connection to or some, if it is an important driver of the variable that you're looking at in the troposphere, then it might be an important variable to include in your machine learning as an explanatory variable. And for then you would need also to use it in your machine learning methodology as a training data set. And then hopefully you could the machine learning tool would attribute how much is driven by this stratospheric ozone index, and then also be able then to make predictions when it changes to the next year. I'm not sure if that is though answering your question, but you have to have a long enough training data set of all the variables that might in a physical way affect the variable that you are interested in. And then you have to train your model on all these different drivers to be able to make predictions in the end.
Okay, yeah, so thank you very much, Professor Michela. I think we'll go on to the next talk. If you still have questions for her, you can send her an email or try to contact her some other way. I think she'll be very happy to take up the discussion with you. So now next we have okay, so Bertrand Fankan is our next speaker. Yes.
What is your question? You have sent it. Okay.
Yes, so Bertrand is from Lyon Diop University in Senegal.
I'm going. I need my computer. The latest email I have sent.
That's what I can also
That's type Java.
I can also try to see if I can share
the latest email I sent.
You just sent an email now?
Yeah, like
this link. No,
this one. Go there.
Lecture.
Yeah.
Yeah, the two I can get it. So which one is it?
You have to download. Yes, download it. Yes. Down it, yeah.
How's your battery?
Yeah, my battery is on. It's on.
And then let's go out.
Yes, my battery is on.
Go out.
Yes.
Just open it and then let me have download it quickly.
This one I can.
Yes. And go to view somewhere.
Yeah, and I have to share.
Yeah, and then you put.
You don't put it into template?
Yeah.
Keep it on the PDF? Is it powerful?
It should play. I hope so.
You have to go to this file and then there is full presentation as slideshow.
Yeah, it's not the same as, it's not the same as PowerPoint.
Presentation as slideshow.
Yeah.
Have it. Go back to your presentation. Go back to the PDF. Not the
PDF?
Yeah. No, you are sharing, but you should go back to the PDF.
Yeah.
The one that's out front. Somewhere. There's somewhere slideshow.
Yeah, but
No, you have to go back outside the Zoom link. Get to the file itself. The file.
The file itself.
The PDF.
Yeah, but this is. Yeah. Yeah, that's what this is the file. Which one?
Where's the
This is the top, right?
Yeah.
But why is it Why is it normal? So. Yes. Yeah, but I think he can go on.
What?
I think he can probably go on. Yeah, I don't just say it. But he can probably go on because I'm afraid of messing things up again. Yes.
Or maybe you can do it for me. What you see there, I'll just show you the hand and then move things here. Okay. It on? Hello?
No,
Is it on?
okay, excellent.
Okay. So I'm going to talk to you about something you have also observed, I think. It's air pollution, observation, and the risk. Okay, and I'm going to focus on fine particles. My colleagues who just finished a presentation, we're talking more about ozone. I'm going to talk more here about the fine particles. Yeah. Okay. So this agenda. So I'm going to start with what we call indoor pollution, and then move to outdoor pollution, and then go a little bit about talk about the level of pollution in Africa and the impact. Okay, and then show you a little bit how to make what we call the health risk assessment, and I will close with a case study. Well, when we talk about indoor air pollution, we talk about the pollution inside, I mean, a closed space, whether you are in a building, in a classroom, or in a car, or in a plane, for instance. Okay. And when we talk about household air pollution, it is when you are in your room, okay, at home, okay, because you know that this is a very specific type of building where you have the living room, you have the bedrooms, the toilets, and everything. So we focus on that now, and I will let you know what happens when we are in the African context. Well, let me first talk about the indoor air pollutants. What can we find indoor in our home as pollutants? We can find volatile organic compounds. These are chemicals emitted from house products like paints, cleaning agents, glues, carpets, and furniture, for instance. We can have formaldehyde. We can have particles. We can have also carbon monoxide. We can have carbon dioxide, or radon, or biogenic pollutants. And when we talk about biogenic pollutants here, we are talking about viruses, bacteria, pollen, and so on. Next, please. Well, here I've listed here a number of sources that you can have. You can have the fuel combustion. When you burn the fuel inside the home, it emits some pollutants. And here you can, when you burn the gas, the GPL, the biomass, the charcoal, etc. So you produce also pollutants. You can have the cooking processes itself. It depends. What are you doing? What type of cooking methods are you using? Are you boiling? Are you frying? It depends also on the type of the cooking or the meat or the meal that you are cooking also. And the building materials. So what type of material have you used for your home? Is it concrete? Is it wood, the glass, the stone? What type of material have you used? The floor materials also matter very much. It can be wood, it can be the vinyl, it can be the tile, it can be linoleum or carpeting. And the furniture, I mean the tables, the chairs or carpets, it depends on the material you are using also. Okay, so these produce pollutants also. And you have also the insecticide, the sprays, okay? When you use some coils, okay, against mosquitoes, for instance, you produce also a lot of pollutants. People are using coils. They feel that they are safe because they are not being bitten by the mosquito, but they get also, they inhale some products also, some pollutants also. So you should be careful. No. Okay. We have also some appliances. The incense. Here in Senegal, for instance, a lot of people use incense and they feel that they have the good smell in the room, but it's also polluting also. It can bring a lot of trouble. Okay, so respiratory diseases also. This is something that's very dangerous also. You have tobacco. There are some who smoke, and when you smoke, you are not just contaminating yourself, but also those who are around you. Okay. Next, please. Well, let us focus a little bit on biomass combustion. Biomass combustion in Africa is an important source of indoor air pollutants. Okay, this is very known. And when you look at the map, and you see that, I mean, 70% of Africa is using biomass for cooking. At least 20% of Africans. Okay, this is what we know now. Biomass combustion, there we have, you can use biomass for cooking, but also for heating in some places. This is what we do. Okay, biomass processes, you can also transformation of wood into charcoal. This is something that people do also very much in some places, and it produces also some pollutants. You can use some solid fuels like wood, animal dung, crop residues, and charcoal, etc. So all those solid fuels produce pollutants. Our forests and savanna, okay, we have a lot in Central Africa, okay, where the climate is very suitable, and that's why people are using biomass because it's available. This is what we realize, and this also biomass also is biomass cell is also an important source of income for many households in those areas. Now, sometimes people think that it might be easy to change from biomass to something else, also gas, etc. But this is not very easy to do because you need some conditions to be fulfilled. Okay, in order to shift to cleaner fuels, it depends first if the fuel that you are going to bring is available. This is very important. And you need to know if people have the money to buy. This is also important. And sometimes those who are using biomass, they are using because they don't have a good processing power. Their purchase power is very low sometimes. So if you are bringing to them gas that they've been using, they'll be buying maybe every 3 months, they can be in trouble. Okay, so you should be careful when you think about some solutions sometimes. So economy plays a very important role when you want to shift from one fuel to another. Okay. Now, I want to talk about a type of outdoor pollution now that is the pollution from traffic. So before, I want to define what is outdoor air pollution. So outdoor pollution is the pollution that happens out of the building. This is out of the building, out of the cabin, okay? And one type is this one that we call the traffic air pollution. So when you see some cars or some planes moving, sometimes they're using fuel and they're polluting at the same time, and they're polluting, okay? And when we talk about transportation, we don't talk just about our cars, but it's everything that moves and then use fuel to move. Okay. Next, please. Well, let's look a little bit at the emissions from the road traffic. So we have two types of emissions. We have what we call the exhaust emissions. This is when you have the combustion, you use the diesel, you use the gasoline, you put it in your car, and you turn the key and start running. And once it's running, you can see what you have here on the pipe. So there is a release of lots of pollutants. You have the CO2, you have some particles, fine particles that are also emitted also. You have the organic water components, we have the carbon monoxide, a lot of particles, a lot of gases or pollutants are being emitted. And if the fuel is not of good type, it can be very dangerous. If your engine is also very old, it can be also an engine, because when the engine becomes very old, it means that the efficiency of the combustion is not that good. Okay, so you can release this type of gas that you are seeing, that fumes that you are seeing. And we know that in our cities in Africa, this is very common. We all know that here. Well, now we can also what we call the non-exhaust emissions. So non-exhaust emissions means that well, it's not from the pipe, but it can be from the car itself. The tire can degrade when they move. Sometimes for those who have cars, you can see that sometimes your tires, you need to change them because okay, they cannot move very well again because they are damaged. They degrade with the time. So we need to change at some point. And when they degrade, they produce also some pollutants. This is very important. And also, it depends also on the type of the road on which you are moving. Is the road paved or unpaved? And we know that this type of road, this is very common in Africa. And most of our roads, I would say something like 70% of roads in Africa are this type of roads. In Africa, it's very, very common. And if you are living there, then you are in trouble because every time you find dust in your house. So those who lives on just areas know very well what I'm talking about. Okay, so these are some sources of non-exhaust emissions. Okay, sources also. Next, please. Well, if now we want to check what are the different types of pollutants that are being emitted by the traffic, there are a lot of pollutants that have been emitted. So we can have the black carbon, the carbon monoxide, particulate matter, you have the nitrogen oxide, the benzene, the BTEX, okay? So a lot of them are being emitted. So it means that if you are driving your car, then you are polluting by force. Whether you like it or no, you are polluting when you are moving. Maybe it's better to move with your donkey or with your horse than moving with the car if you want to preserve the environment. Okay, next, please. Well, who are the people exposed? So this is a picture I took a couple of months ago in my city, in Chess, where a woman is just sitting close to the car moving. This is a truck moving. So she's just close and she's selling her fruits. And we see this type of picture. We see this type of picture almost everywhere in Africa. But those people, do they know that they are being exposed, that their life is a risk? Sometimes they are not aware. Because I remember when we made this investigation, we asked them, they said, yes, yes, we know, but what can we do? This is what the question, what should we be doing? Okay, so let me give you a little bit some info about the context. Well, in Africa, most of the population are young. I found in statistics that more than 70% of Africans are under 35. So it means that those people are active. They have a lot of energy. They want to work. They want to do something. But unfortunately, the government, most of the time, they cannot provide jobs for those people. So they need to find for themselves what they can do. So they have to look for a way to survive. And that's why you are seeing them on the street, on the road, on markets, selling goods, etc., etc. So this is one of the reasons. Another reason is that this is the urbanization, that almost everywhere in Africa, you see that our cities are growing. Almost buildings everywhere. So there is kind of dynamism. So you reach a city, you see maybe three houses somewhere in some small part of the city, you come there, 6 months after, you see 10 houses. 1 year later, you see 50 houses. It's almost like that everywhere in Africa now. Urbanization is something very important now. And when you talk about urbanization growing, it means that you need to find to supply electricity to those people. You need to build the roads for that people. You need to bring the water to those people. You need also to provide schools and so on, officers and so on. So this is a very challenge for our governments here. So in some countries, they talk about the unemployment rate that would be something like 25%, 50%, but we really don't know what is the right. But what we know is that people don't have job. If you talk about, let's say, good job, have a contract with a company, with the government, how many of us have contracts? Very few people really have contracts, okay, in companies or with the government, most of the time. And that's why you will see them, okay, most of the time on street, in villages, trying to do something, okay? So those who are selling goods along the streets, selling fruits, selling shoes, selling a lot of things, goods along the streets, they are exposed, okay, to these fumes from the vehicles. Not only fumes, but even the temperature sometimes, 45 degrees, they are there selling goods because they need to survive, okay? Well, so next. Well, what makes the situation worse? The lack of roads. I said it, that that's 50% of our roads are paved. This is the situation in Africa, okay? And those roads, not only that are missing, but also those who exist are poorly designed and they are not maintained. And you can confirm it, that most of our roads are not maintained. Most of the time, they are not maintained. All car fleets in Africa, when you look at the average age of the car fleets, it's around 20, 25 years. While you look in Europe, it's something like 5, 7. But in Africa, it is 20 years. This is average. It means that if you take all the cars and look by categories, as we did in Saudi, you find that, okay, you have the trucks, they are very old, sometimes 40 years old. Yeah, 40 years old, some cars. And we look also some taxi cabs also, 30 years, 35. Yeah, okay. Traffic congestion, yes. See, if you don't have a lot of roads, the small number you have, they are congested most of the time. In the morning, at the midday, in the afternoon, in the evening, they are most of the time congested, especially in cities. Increased import of used vehicles, yes. We keep importing used vehicles from Europe, from US, from Canada, and so on. And those vehicles, when they finish their time there, they're shipped to Africa, and we continue to use. And they never die in Africa. So now we are having a new phenomenon, that is the increasing number of tricycles and bikes from China now. Since they are cheap, people prefer, since they cannot buy a car, then they buy a tricycle or they buy a motorbike. So in villages now, you see how people are using motorbikes almost everywhere in our villages now in Africa. And those tricycles and motorbikes from a study that we did, that was a couple of years ago, they pollute a lot more than cars even. This is what people don't know. Poor quality fuels and lack of control. Yes, the fuel sold in Africa especially in West Africa, from what I know from my investigation, it's a poor quality fuel that cannot be used elsewhere. That is being shipped in Africa. They call it the African quality. Yeah, this is the reality. Uncontrolled urbanization and unsustainable planning. Yes, our cities just grow without any planning. One day, one morning you wake up, somebody has put his house just close to you. Who are you? Why are you here? We don't know. There's no road. There's no electricity, nothing. Just up. The cat family is there. I've settled. After 1 year, another one comes. After 3 months, another one comes. It's always like that. No planning, no roads. And then at the end of the day, he comes to ask you, please, can you allow me to pass through your door, please? Because I don't have a place to cross to reach my house. Yeah, it's what we see every day. Lack of automotive industry. Yes, unfortunately in Africa, we don't have an automotive industry. It is at a very, very, very infancy stage in Africa. We have some companies that are just starting, but are not well, competitive, like the Chinese companies or European companies. We have IVM in Nigeria, Katanka in Ghana, but they are just at an infancy stage. So it's not that easy because it is a business that needs a lot of money to start. Lack of regulation. Yes, we need regulation. We need regulation. There's no regulation on cars in Africa. You bring your car, it can pollute. Nobody will ask you what's happening. So we just pass. What they need, you pay the insurance, and it's okay. It's okay. You can move. It's not like that elsewhere. Just in Africa that we are seeing that. Next, please. Now, let's just go to the particulate matter. So the particulate matter are some specific types of particles. We talk about particles of very, very small size, and we put them into 3 categories. We have what we call the coarse particles, okay, with diameter between 2.5 and 10. The fine particles with diameter below 2.5, and we have the ultra fine. So just 3 types. And what we do most of the time is that we focus more on this. I'm not saying that we should not be focusing on coarse particles or not on ultrafine. No, but most of the time, if you look at the literature, we focus more on this. Even though there's a debate now, people are thinking that we should be going and investigate and make more investigation on ultrafine. I will tell you why later. Coarse particles, well, sometimes we do a specification on it, but not as on fine particles. Okay, so this is a comparison that I put there so that you can see how they can be different. Okay, next, please. Well, what we do when we are making our investigation first, if you are to work in this field of air pollution or air quality, you need to know how to use these instruments. Okay, because this is the beginning. I'm talking about those who are interested in making measurements or doing some ground measurement. This is what I'm interested in. I'm not on satellite data and so on. I see myself with my eyes than to see what people have measured up there. Okay, I prefer to focus on this. It is around me. I can see it. I can feel it. Okay, so for those who would like to do ground measurement, so you can use what we call here the local sensors. You can use this type also. These are the portable monitors, or you can use the high-grade monitors. These are the 3 types we do. So in Africa, we don't have a lot of money. So what we do now, we are trying to be a little bit smart in Africa now. So we focus on this one because the price is very low. Okay, then we take this one, we calibrate, we take the data, we compare with this one. This is what we do now. We call it calibration. Okay, you compare the data, and you can use machine learning, AI, and so on in order to improve the quality of your data. So this is what we are trying to do, and that's why, if you look into literature, the number of publications in Africa in air quality is increasing because of the fact that we are using this now, now in Africa. Okay, so this was a chance for us because we don't have money. For those who are looking for high-grade monitors, they cost a lot. You can see the price. They cost a lot. So instead of using this, we use this 100 euro instead of 30,000 because we don't have money here. So we want to be a little bit smart. And machine learning AI can help a lot. Okay, here. So this category also, I've been using this category. They're also very good. These portable monitors, I bought some. But the problem with them is that they use battery. And sometimes they can stay for maybe, let's say, 5 hours or 10 hours, and then they go down, you have to recharge again. Okay, this is the problem. Next, please. Well, this is a map that I took from a report from a colleague who works in the US at the Health Effect Institute. So these are the places that the places are in red are the most polluted places in the world, and you see where is Africa. You can see where is Africa. So it means that the level of PM 2.5 in Africa is really high in comparison to the rest of the world. You can see. Next, please. So if your environment is polluted, what can be the consequence? There are a lot of consequences that can happen on the environment, on the economy also, but I prefer to focus on health, okay? And here I said, almost all parts of our bodies are affected. So in the past, we didn't know that the fine particles, okay, in particular, were correlated with concentration, were correlated with a lot of diseases. But now we're having new studies every day that confirms that a lot of diseases, okay, are associated with fine particles. So some of them are here: respiratory issues, asthma, and so on, cardiovascular problems. Okay, we are having more and more cardiovascular attacks now. Okay, in our hospitals, if you go there, you will see. And just of recent, we discovered that it's a link to fine particles. We didn't know in the past. Allergies, lung cancer, cancers. So this is very important. Tissues, impaired cognitive function. Impaired cognitive function, this is for those who are young. We discovered just of recent that for women who stays very close to in areas that are really polluted, the fetus can be contaminated also. This is what we found. So this is important to know. And also concerning the young people, sometimes you see some schools that are being built just close to the roads. Those children can be impacted negatively if those particles can flow inside the classroom because they stay long in the classroom. Their brain can be affected also. Their cognitive faculties can be affected. This was also demonstrated. Okay, and increased mortality. So I will not add more. Go back, please. Well, we have back. Yes. Okay. Good. Yeah. So, please. Oh, I'm not yet started. Well, you have short-term effects and you have also long-term effects. Short-term means you are exposed for a few hours, just few hours. Okay, few hours, few days. What long-term means, you can be affected, you can be there exposed for many years. Like those who sell goods around the street, they are there for many years, most of the time. Okay, next, please. Well, in Africa, this is what the report says: 1.1 million deaths a year due to fine particles in Africa. Okay, and when it comes to the ambient PM 2.5, 5 out of 10 most heavily polluted areas or countries are in Africa: Nigeria, Niger, Egypt, Mauritania, and Cameroon. This is what the report says. Okay, and now here you see this is the mortality here. Okay, we see that those who are affected the most in DR Congo, for instance, are the infants here, and those who are old here, and they're affected by what? By household air pollution. While when you are in Egypt, it's the ambient, not the household pollution. Okay, and you can see the infant here is not that high as in the Congo. This is the difference, and you can feel the difference here. Next, please. Well, we are going to talk a little bit of toxicology because we are going to go to the risk assessment. Well, when it comes to risk assessment, you have four routes for the exposure. Okay, the inhalation, the ingestion, the skin, and then the eyes. These are the four main types of exposure that we have. And the duration, I just talk about it: the chronic, the long term, or the acute, that is the short term. Next, please. Next, please. Next, please. I'm close to the end. I'm close to the end, please. Well, so when it comes to the inhalation process, so it means that you are going to take the particles from the nose or from from the airways. And now you have different type size of particles. So when the particles is small, it goes very downwards. It's big. It stays here on the nose. This first part. As soon as they become smaller, they go deeper down in the lungs. Okay, this is what happens. Next, please. Well, when you want to assess the risk, we have what we call the probabilistic risk evaluation. Then you can evaluate, okay, the risk for non-carcinogenic and for carcinogenic. And these are the formula that I put here. I don't want to go deep into it, that you can use. And here, in this case, when it comes to non-carcinogenic, you calculate the HQ, the hazard quotient. If it's more than 1, then you are at risk. And for the other case, for the cancer, if you are more above 10 to the power minus 4, then it means that you are at risk. Next, please. Well, in my city, in Thiès, we did some study, okay, where we said, okay, we are going to see what happens with those people sending goods along the street, and then we're going to see what happens. We went there, we made some measurement, and then I will show you the results. Next, please. Well, what we did is that we have chosen a route like this, 10 kilometers, okay, in the center of the city, and we put the monitor, and then we say, okay, we're going to measure and see what happens. Next, please. Well, this is what we had. We had 10 locations, okay? We measured the concentration of fine particles, and these are the results. So we see that here, for instance, the HQ is above 1, and we see that the LCR is above 10 to minus 4. So it means that they are risk. So whether this is for cancer or for non-cancer diseases, they are at risk. Next, please. This is the end, I think. Thank you very much.
Okay. Do we
take questions, and then the next one, I'm trying to shift the presentation after lunch.
Okay, Maria, do we have questions online? Okay, so we can start with the online question.
Okay, great. Thank you so much for that excellent talk. So we have a question from an online attendee. They asked, how do you monitor indoors pollution separately from outdoors pollution? Are there sensors in homes? Is there any historical data set for indoors pollution?
What I saw of recent from some colleagues from the UK, they were trying to make what we call the source apportionment, knowing what is being produced inside and what is produced outside. So what they do basically is that they put several sensors inside, in the bedrooms, in the living rooms, okay, and they put some also outside, and they can compare, okay, and they can compare the concentration that we have outside and see how they move, and they can say, okay, this is from outdoor, this is generated indoor. Yeah. Yes, yes. Well, it depends. It depends. If you are in a situation where you are cooking, for instance, inside, it means that you are going to generate a lot of pollutants at some point. And when you cease, you see that it will decrease. So the concentration will decrease. And also it depends. If outside, for instance, it's the morning and the road is busy, so a lot of particles are going to flow inside. Okay. And also it depends on the windows. If it is tight or no, or the door is tight or no. It depends. A lot of parameters that can have an influence on the indoor pollution. What is outdoor, you cannot do anything. But if you are inside your room, you can say, okay, I'm going to close my door, I'm going to close my windows, and then could be maybe safe inside. But when it's outdoor, sometimes you cannot do anything. If you have vehicles moving, what can you do? Can you stop them? No. Yeah.
Do we still have questions online or questions in the room? Or who has not answered, ask questions? No. So what I think is we can take just a few questions, and then since Bertrand is here, we can continue the discussions over lunch and for the rest of the days.
Thank you. Thank you, Bertrand, and congratulations for this very clear talk. So my question is, if I wonder if in your work you separate anthropogenic and natural pollution, and if so, how you separated these two pollution? Thank you.
Yes, here I have not made any distinction. I just put my monitor and everything that passes, I just measure. Yeah.
Maybe one more question, and then maybe someone who has.
Give them all they ask, and then see if there are similarities of the question.
Okay. Now throw all your questions at him at once.
Thank you. Okay, you were mentioning, okay, Africa, we don't have money, we are not rich, I want to believe that Africa is blessed with many natural resources. As much as lack of resources is a challenge, I think government policies, prioritization, and yes, are equally as important to consider in these kind of things. And I want to believe that most African countries do not have set consequences for actions. Like they don't penalize if you do something bad, like we see in developed countries and developed world. So I want to believe that lack of resources is not a major setback, like would really affect this policy. Thank you.
Yeah, so regulations. No, we come to you. Just note the questions.
Yes, go on. Okay. In my case, it's like when you present the impact of climate change for the human action, they are the part of climate, like climate adaptability. So it's to remind to the government to apply this part. So we create the green park to create some place to help to reduce the impact of industry in our life of people. And then I have the question about how can I build your own sensor? Because you have the material, you have my microcontroller, you have everything, you have the smart people. Why cannot be your own? Why?
Okay, so you noted that. Probably go into discussions later on. Oh, sorry. Yeah. Yeah. So you can respond like
yes, very quickly. Yes, I start by the last question. The last question on the solutions. On the solutions. Okay, the solutions, yes, we know what could be the solutions. Like for indoor, for instance, a simple solution could be, for instance, to put some plants inside. We call it phytoremediation. This is a solution. And it means that also our cities, we don't see trees no more in our cities. They are cutting every day. They are just putting bridges. This is not good for us. This is one. The other one was about why don't we build our own sensors? 2 years ago, I organized a workshop on that to teach people how to build their own sensors. So you can also do that. Okay. The other question about the resources. Well, when I say that we don't have money, I say I don't have money. Okay. I don't have. I do with what I have. But I do believe Africa is not poor. Are you getting me?
Yeah. So let's thank Dr. Bertrand again.
Okay, everyone, we have lunch, and please note, don't forget, once you make the buffet line and you enjoy your meal, after, take your plates when you're done to the back side where someone will take your plate and put it away. And what time should they be back at?
We'll be at 2:45. Okay, we'll be back at 2:45, and there will be a presentation from Professor Carl, who is from NASA. He was willing to shift his talk. So let's try to do it faster. Then you can have enough time to discuss. Okay, thank you. Let's thank also all the speakers of the day, all of the morning sessions. Thank you online. We will be back soon. about 2:45 UTC. Yeah, because we then run after.
So it will be in the afternoon.
Or maybe tomorrow. Let me check. Okay, maybe tomorrow during the, yeah, let's see. Yeah. Combiné? Recombiner?
Quel truc? C'est moi, non, c'est David, non?
Recombiner?
Il faut que je modère ça, c'est sûr.
Ouais. dans le programme, n'est-ce pas? OK, so là. Sangadev? Sangadev? Sangadev, you said? Sangadev? Sangadev? Ni Nangadev? Okay. Sangadev. Mangi. Mana? Mana? Okay. Yeah. It started at 45. And we have do you have the agenda? Yeah, I think. You have presentation of Professor Malik, and then you have the discussion. Okay, so this one. He's online. Okay.
Yes, yes.
Hello. I think the room is muted. I can't hear anyone if they're talking. I don't know if you can hear me.
Yes, we can hear you, but it's like nobody is speaking yet.
Okay. I'll wait on the line until they're ready.
Okay, thank you.
Now it should be okay.
Okay.
Do you hear
Yes, I
us?
can hear you.
Okay.
Yes, I can hear you. You can hear me, I suppose.
Okay, it's fine, Carl. Are you hear us?
Yes.
Okay, great. So we will give the floor to Carl Malings for the talk about the forecasting and reanalysis from the NASA Global Modeling and Assimilation Office, available product, data access, and uses cases for AI and ML. So, Dr. Carl, you have the floor for about 30 minutes. Thank you.
Okay. Okay. I'll try to keep this brief. I know we were a little bit behind schedule, so thank you for the invitation.
Sorry, Carl, you have
yes.
just 20 minutes. 20 minutes.
20 minutes. Yes. Yes.
Thank you.
Yeah, I'll try to keep it brief. So in this presentation, I want to briefly introduce some of the products available from the NASA Global Modeling and Assimilation Office, and give a demonstration of how to access the data, which might be useful in your training here, as well as your broader research. To introduce the NASA Global Modeling and Assimilation Office, this is a part of NASA, an office within NASA, which is responsible for making use of NASA's observational data, especially satellite data, to understand, analyze, and predict changes in various Earth systems. And this is done through the combination of modeling of these systems with numerical modeling, as well as data assimilation. I believe in the morning you had a presentation that went into data assimilation and reanalysis products. So I'll just briefly go through this introduction since you've already heard it. But the basic idea is that we can bring together a background or prior from a model of a system together with data from one or more observing systems, for example, satellite data, balloon data, ocean floats, and so forth, various sources of measurement data. We bring this together in the data assimilation system, and it provides us an innovation or an update, which we then apply to the model to create an analysis or a posterior. This is basically an updated condition of the model to bring it into better agreement with the data collected by our observing systems. So this is the basic approach that this Global Modeling and Assimilation Office takes to understand the Earth system. And it's implemented in a family of models collectively called the Global Earth Observing System, GEOS, sometimes called the Goddard Earth Observing System after the name of the center where this office is located. But this GEOS Earth System model is the basic framework that we apply, and it's applied in a variety of applications, as you can see on the slide here. In this presentation, I'm going to focus on 3 specific applications and products from this GEOS system, just briefly introducing them and then hopefully giving you an example of how you might go about accessing the data from these. So they're summarized briefly on the slide here, and I believe you'll have access to these slides so you can look at this in more detail at your convenience. But just to briefly go through them. So the first one is called GEOS FP. FP stands for forward processing. And this is the implementation of the system in a near real-time weather forecasting mode. So this system is run every day, actually twice a day, to produce both a 5 and a 10-day forecast globally of mainly the atmospheric state, but also including other parameters of course, including things like aerosol concentrations, carbon monoxide concentrations as well. You can see in the image here an example of the data forecast from this model for the different components of aerosols around the world. So this is mainly used as a weather forecasting model, and it's kept up to date with regular updates to keep it in line with new advances and take into account the latest data from new satellite missions and so forth. The second system or model I want to talk about is called GeoCF. The CF stands for Composition Forecast. And this is an application using the same underlying GEOS model for meteorology, and then coupling that with the GEOS Chem chemistry simulation system. And this allows us to simulate various reactions between gases in the atmosphere and also the formation of aerosols. So as we heard earlier in the day about the importance of ozone for the climate system and for human health, the importance of aerosols for human health, that's the main focus of this system. It's run every day, and it produces, in this case, a 5-day forecast, tracking about 250 different chemical species and more than 700 different reactions between those chemical species. In the animation, you're seeing sort of a simulation of ozone from the model, as well as some of the precursors to ozone formation, which the model also tracks to enable it to model the formation of ozone in the atmosphere. And the final system, again, I think you heard about this earlier. It's called MERA-2. This is the Modern Era Retrospective Analysis for Research and Applications, version 2. And this is the system run in a retrospective mode to look at creating a reanalysis data product. This product is available from 1980 to a few weeks behind real time. And it's suitable for sort of long-term reanalysis applications, as you heard about this morning, including things like aerosols and stratospheric ozone as well in the simulation. So that's a sort of a brief overview of the different systems. Again, if you have more questions, you'll have access to the slides. I want to try to switch over to sharing another window here, just to give a brief demonstration about how to access this data. So I'll start with here, the GMAO webpage, gmao.gsfc.nasa.gov, or if you search for NASA GMAO, this will probably come up. But this is the web page for the office, as I mentioned, and you can, from this page, access the various data products. So one particular way to do that, if I go to this Explore tab, there's a list of GMAO products here. If I click on that, this is sort of a list of the publicly available products. You'll see the GEOS FP, GEOS CF, and MERA-2 that I mentioned, as well as a couple of other products which I didn't discuss here. For example, this is a subseasonal to seasonal forecasting model. If you're interested in those kinds of longer timescales for forecasting, that would be the place to go. Just to illustrate, I'm going to click on the MERA-2 example here, and that'll bring me in a moment, hopefully, to the MERA-2 web page. And this will have links with other information about the data product. It's taking a minute to load here. So this is the landing page, and you see links on the left. Documentation, of course, if you want to look into the details of the model, frequently asked questions. I'll go here to the data access tab, which is going to kind of point to different methods to access the data. And there's two I want to briefly showcase here. The first is a visualization tool. So the GMAO maintains an online visualization tool, as shown here for all of its, or for most of its products, rather. You see at the top, there's tabs for weather. This would show the GEOS FP system. There's a tab for composition. This would show the GEOS CF system. And I'm right now on the tab for reanalysis, which shows the MERA-2 system. And there's a variety of options for visualizing outputs of the model. Just to demonstrate, I'll click on this anomalies option. You see various maps here and various parameters. So for example, if I want to look at the soil moisture, I can generate that, and I can change my region from CONUS to Africa, for example. And it will bring up a plot of the monthly anomalies. You can select the month and year down here. So it's showing the monthly mean soil moisture for October 2025, which is the last full month we have data for, compared to the climatological mean from 1991 to 2020, the anomalies, the difference of these two, and then the standard deviation to get a sense of the variability. So there's various other plot options. For the sake of time, I won't go through everything, but just to give you a sense of this tool for visualizing some outputs of the model. Going back to the page, if you want to actually access the data themselves, there's another link right here, which I'll open. And this will bring us to the data center that actually hosts all of this data. There are various options for searching. There's various filtering options here. There's a search bar at the top. So you can use those to search for data. I'm just going to go type in T2M, which stands for temperature at 2 meters, which is one of the products offered by the MERIT-2 dataset. And that will bring it up here. If I click, I can see more details about the data set, links to documentation, the list of variables contained in this data set. You can see the many variables here, including 2 meter temperature and so forth. And for data access, there's some options here. So various options. I'll click on this bottom one here just to show what it looks like. If I click to get the data, you can pick different options. You can get the full data files, or you can subset the data to specific time ranges and specific regions of interest. So you just download the data you need. You don't need to necessarily download the entire data set. So this is one method for direct access to the data if you want sort of full data files. In the few minutes I have, I want to show another option called Giovanni. And this is an online tool for accessing and performing basic analysis with data available on this data center, including the MERIT-2 data. So because I started from this particular data set, when I clicked on the button, it brought me to the subset of variables contained within that data set. And this system is really for performing certain simple online analysis without having to download the data yourself. So for example, I can look again at the 2 meter temperature. I can select that. I have some basic information about this variable. The units I can adjust from Kelvin to Celsius if I wanted as well. And it gives me some options for creating basic informational plots. So I'm going to show just a time averaged map, just as an example here. I can pick a date range. So for example, January 2000 to maybe 2015, maybe let's say December 2015. I could pick a region of interest using this map tool. Let's just draw a box around Africa here. And I can click the button for plot data. And what this will do is it'll go and access the data online, perform the averaging over the time interval I mentioned and for the area I mentioned, and it will generate a plot. You can see that that didn't take very long to generate. You can see now an example of the result of that analysis described at the top. So this is the average of the 2 meter air temperature from January 2000 to December 2015 for this region I indicated. And you can use these options to change some of the plotting controls. And then importantly, if you use this download button here, you can download the result in various formats, either as an image itself or as, for example, a netcdf file if you want to take this data set and do your own analysis. So again, the advantage here is I didn't have to download the entire data set. I did this subsetting and this averaging online, and then I can just download the results of that analysis rather than the full data set. So that's a way to simplify that. And there are various other plotting options. I opened a couple before the presentation. I sort of generated this just to show the example. So this is the same analysis. There's other plotting options. For example, I can do, instead of an area average, I could do a time series like this. And again, download the result as, for example, a CSV file or a netcdf to do my own analysis. So I think for the sake of time, I'm going to leave it there. Again, you'll have access to the slides, and I'll hopefully be able to answer questions during the discussion, but I just wanted to illustrate those methods of data access because I thought they might be of interest to this audience. So thank you very much, and we can go to some questions. I see I have a question in the chat, but yeah, I'll let you ask questions. I'll let you take it from here. Thank you.
Thank you, Kat. Thank you for this great talk. So maybe we will take two or one question before the panel discussion. Go ahead.
Yeah, thank you very much for your presentation. My question is about the, is there any open API for the Earth data platform?
Yes, I didn't talk about that in this presentation, but if you go to the links in the slide, so Earth data is the general platform for accessing all NASA data. So not just the Merit-2 reanalysis that I showed, but satellite data as well. And they've implemented a couple of APIs for basically this search service. You saw, I gave an example of like selecting by region and by time frame and by data product. So they've implemented some APIs that that implement that sort of a search process and will return to you either a list of files that meet those search criteria, which you can then go and download yourselves, or in certain cases, they have also implemented that subsetting option where it'll actually go create a subset of the data based on your query and just return to you the results of that data analysis. I think, yeah, there's would be further information and documentation of that on the Earth Data site. But yes, short answer, yes, there has been some implemented for using an API to do this sort of analysis or this sort of data searching.
Good. Okay. Is there documentation about the API for that?
Yeah, maybe during the discussion as we're switching over to that, I'll search and I'll put it in the chat so we have
Sounds great.
access to that.
Excellent. And then I'll go ahead and take one of the questions from online. I'll read out loud so that the folks in the room can hear it. So the question is, how accurately can satellite-based hydroclimatic variables such as precipitation, evapotranspiration, snow cover, soil moisture be used to predict stream flow in ungauged basins, and what modeling approach provides the best performance under data-scarce conditions?
Yeah, so that's a very good question. It's not my area of expertise. So again, I think during the discussion, if there's no questions for me specifically, I'll try to search for that and come up with a better answer for you. But there is a NASA related project which is trying to do basically what you were asking about, which was sort of translate our best estimates of these evapotranspiration parameters from satellite data into things like stream flow. And of course, again, this isn't my area of expertise. This is sort of secondhand from what I've heard from that team. But of course, it's very difficult to do that in areas where you don't have streamflow gauges to calibrate against. So they've had some success, but of course, it's always a challenge in those sort of data scarce areas. And what modeling approach provide the best conditions under data scarce conditions? Yeah, so I don't have a specific answer to that, but I'll try to find you links to that project, and hopefully either through those links or maybe contacting that project team, they might have a more specific answer for you.
Last question for the panel discussion.
Thank you. I was trying to download some data from NASA, IMERGE, and MSc. And I noticed that we can't download since the decision from Trump rules. So I don't know if this decision will affect your website or what happens really.
Yeah, I mean, that's a good question. So I'll say in general that, all this data all the NASA data should be publicly available as per NASA's rules up to this point. The data should all be freely publicly available. With the recent government shutdown in the US, there were some interruptions in service for some of these systems. Recently, that shutdown was ended and those services should be being restored. We have another I guess, decision point in January where there might be another shutdown which might again affect these things. So to my current knowledge, there's no plans for any changes in those policies for the data not to be publicly available. But with these interruptions in service, there could be specific, problems with running some of these systems. But yeah, if you had tried this in the last few months, you might have had some issues just because of that reason. But yeah, in general, I'm not aware, from my point of view, at least, I'm not aware of any plans to make changes in the public availability of the data.
Okay, thanks, Carl. I will ask the last question. I say that you share with us some data assimilation system like CDVAR, CODIVAR, and my question is, what do you think? Basically, what is the add value of a CODIVAR about CDVAR? What you can talk about?
Yeah. So again, it's not perfectly my area of expertise, the data assimilation science of it, but I'll try to answer as best I can. So I think the main difference is, in 3D variational data assimilation, you're considering the 3 spatial dimensions, and the 4D VAR brings in the temporal dimension. That's my understanding of the basic science and the basic difference. And so you're really able to take advantage of temporal correlations in things. So certain variables change at relatively slow rates, so you can take advantage of data collected before or after a given time to create a more smooth sampling. The challenge there is it's a much more computationally intensive to consider that additional dimensionality. I think maybe I'll leave it there, and again I'll try to find you a reference that goes into more detail, because it's not the data assimilation system specifically is not my area of expertise.
Thank you. So you will stay with us because we have a discussion panel. Yeah, go ahead.
Yeah, just before the panel discussion, I think we would like to introduce Eric. Yeah, he's coming from University of Rwanda, and he was developing an instrument to measure the indoor air pollution. So yeah, I think Eric, are you online?
Yes, I am online. Can you hear me?
Yeah, you have 5 minutes, and then this actually.
Nanga Def. So can I share a little bit my slides?
Yes, go ahead. Go ahead. Then we can continue the panel discussion right away.
Can you see my slide?
Yes. Yes.
Okay, thank you so much. I'm here just to present, I have 5 minutes, but I'm here to present the device that we have developed, which is a clean city IoT air device, where we were looking on the problem of the air quality, especially when it comes. Yes.
Okay, we are seeing your screen, but can you go to the slide mode for screen? Presentation.
Slide mode screen. But I'm not sure that this one.
Yeah, you can go to.
It's okay. Now wait.
Design.
Until your network in Rwanda is loading in Senegal.
Can you see it now?
Yes, but it is not in presentation mode.
So when let me check.
Try with design.
Actually, yes, that one. No, the previous one.
Last one to the right.
Yeah. No.
This is okay now?
Yeah, press that one, yes. And then maybe wait.
Yeah, it's fine.
Okay.
Great. Go ahead.
Go ahead.
Okay, thank you so much. I was talking that it's a device that we developed especially for African cities, where we need to deal with the air quality in African cities. And I'm not going to back again on the story, the background story of air pollution, where it is one of the toughest, most critical societal challenge, because I'm sure that you have got all most of all those background, where over 7 million deaths per year are dying due to the problem of air pollution, and 90% of the world population are exposed to air pollution, coming together with different disease, as you can see with their percentage. And but I need to talk more about the short-term exposures, and because they are dangerous, and sometimes no one is caring about them, because most of the existing system are the standalone system, and then they will be able measuring the air quality, which has already expanded, and we need to know the source of those short-term exposure with high peaks, and then we need to monitor them, because the researchers have shown that they create lower IQ, especially for the kids, and also amplify the disease. And that's why most of the time we need, most of our research was more about working on the short-term exposures. And today, of course, emitters of the air pollution, they are not penalized, and we need to know who is protecting, at which level that is protecting. So when it comes in the cities, especially in Africa, last year I was in Senegal, and I remember that my air was more good there. So because I was having a lot of particle matters around, it's not only in Senegal, but in other cities in Africa. So we have a problem of air quality, and especially here in Rwanda, where we are conducting our research. The city is growing, and we have a lot of population, and the traditional centralized monitoring system are expensive, and also they are limited for the coverage, and they are exposed in some areas. So we need to think something which can be mobile, and there is then a need of real-time, scalable, and cost-effective solution, especially for Africa. So our project was to develop a clean city IoT, which will be a scalable framework using IoT and mobile network. So they monitor about air quality across the Rwanda currently, and we utilize low-cost sensors and mobility. This is our system architecture. Probably someone who maybe went to know more about it. So probably we have the microcontroller and the sensors that we have put. We have the GSM and the JSON data, and also we have the different protocols that we are sending data to the cloud, and also we have here down the way of that we can get the notification as well as the web dashboard. So we are measuring the 6 pollutant, and also we are doing the location target for the spatial analysis. So this is the device. I have it here in the lab. I'm in the lab, by the way. And internally, this is how it looks like on this side of my light side. And when it is on moto, so it used to be there, or we used to put in front, and then you can be seeing those smaller numbers, which will be showing all those variables or that we are measuring. On the car, we also fixed on the car, and then to be able to be the same. So we also do the data analytics, where the data are aggregated in cloud-based on system. So we have put a machine learning model, and we are using the time series analysis, and we are trying to detect the spikes, and also looking to the trends across the city. We only don't have a lot of devices. We only have 10 devices. Here, this is the correlation among all the features, and here this is how the distribution is look like on all those field features, as they are 8. They are 8 because we added also humidity and temperature, and this is we piloted our device in Kigali, and it's showing high performance with low maintenance, and also it's something that can be reliable based on the comment that we got in the last month of October when we were launching it. So it's utilized existing mobile network infrastructure. We don't need new ones, so no proprietary network required, and also it is nationwide scalable And also it's engaged the public because now everyone will be having the device will be able to go online and then find the dashboard and then looking how the maps and the arrays that he may be wishing. And then it promotes environmental awareness because the people will be knowing how the climate look like. So in conclusion, the Clean City IoT Air device offers the transformative and scalable solution. It empowers cities and citizens through the real-time data. And Rwanda, we are serving as the model for the other African country. And we hope that we are going to expand the project to the other country in Africa. So these are the team members, and this is the some of the partners that we have, where we have University of Rwanda, of course, where I'm staying, and we have the LEMBA, our environmental. Here in Rwanda, we have different private institutions. We have National Council for Science Technology in Rwanda, but at all, this project was funded by PASSET, the Regional Scholarship and Innovation Fund. And my quote every time when I'm presenting this, I'm saying that even if our lungs are already damaged because we have been exposed to air pollution, but we still need to save the next generation by preparing the way that they can have a good breath and a good air. Thank you so much, Jaleje Murakoze in Kinyarwanda. If you allow me, probably I can stop a little bit my presentation, and can I put a video? And then I don't know if you are seeing the device. This is the device. Oh,
yes, it's not clear, but almost seen. Yeah.
So this is the device that I have. So I already have it one in the office my lab. So that was the presentation. I think I exceed 5 minutes, and thank you so much.
Thank you, merci,
Jamalek.
Okay, so now we can go directly to the panel discussion. Yeah, so we have the first point about the observation, I think. Okay, so how many panelists we have? Yeah, we have Eric. Eric, you can stay with us about the discussion. We have Prof. Jonathan, have Prof. Yacinthe, Prof. Marceline. Okay, so Prof. Robert Biake. Okay, so Prof. Bertrand. Here, okay, and Dr. Carl. So the first question is about the introduction to Clear City IoT air device, leveraging IoT mobile networks for the urban air quality inside in Rwanda. So it is the first question. Maybe for this question, we can give the floor to Eric. Eric can take the floor.
Yes, I can hear you. I didn't get the question very well. Can you repeat the question?
Yes, the question is how we can introduce the Clear City IoT.
This was his presentation.
Yeah.
So
I think that was the topic that I was presenting.
I don't have the last program.
It's not a talk. It's like it's a discussion. So we have 2 points that we would like to discuss. Is the first one is about observation gaps, current limitations, future needs for constraining weather, climate models, and so on, for informing decision making. Decision making in terms of climate change, climate resilience, and so on. And then the other point is about how climate change is impacting Africa and its air quality. Like, we can think about aerosols, air pollutions, and so on. Yeah. So, the floor is open. This is just for the panelists of today. There was, sorry. Yeah. Okay. So, Professor Bertrand is here. Eric, you're online. I think Carl is also online. So you can just elaborate on this. What are your thoughts? And then we can also initiate the discussion. I think there was already questions that was after the presentation of Bertrand. Maybe we can build on that. What are your thoughts and what you would like to interact? I think that's.
You mean we should start by the last question?
Yeah. The first one is observation gaps, current limitation, and future need for constraining weather climate models for informed decision making. Informed decision making in terms of climate change. I think that if you make decisions, you need really your decision to be informed based on what the climate feel. And the second point, I think this is related more what you are doing, how climate change is impacting Africa and its air quality. Like there will be more dust storms or the ozone pollution or the indoor pollutions.
Yeah.
How climate change is going to I can say exaggerate.
Okay. Okay. So just so this morning I show you a picture, and that picture has a reality. That is true reality. That Africa is one of the places where the level of pollution is very high in the world. Okay, and if we are talking about the burden of disease, for instance, we say that in Africa we are really affected. This is what we can say. From my experience on the ground, making measurement, traveling here and there, discussing with my colleagues in Ghana, in Rwanda, and so on. So what I saw is that the level of pollution is very high in Africa. And why is the level of pollution so high in Africa? It is because of a number of factors that, as I said this morning, we have the demography, we have the urbanization, and we have, I didn't say it, the industrialization, because it's just now that Africa is undergoing the industrialization. If you go in, let's say, how do we call it, a place, Diamniadio, for instance, here in Senegal, almost every day you are seeing a company trying to set up somewhere there. They are looking for land to stop companies, factories in Senegal now. So it's just now that we are seeing that it's almost everywhere in our cities in Africa now. If you go to Lagos, you see the same phenomenon. You go to Abidjan, I think Julien is here, you can tell us more about that. So this is something that is very important. And what we see also is that at the same time, we are seeing people going to hospital. More and more people go to hospital because of asthma, because of cardiovascular attack. And now we know that there's a link between this number of diseases or this rate of disease that's increasing also and the pollution. This is what we know now. That is the correlation. This is what we are sure of. Now, how can this pollution also affect the environment, not only the people, but also the environment? I can say that we lack information in Africa because there is also the impact of air pollution, for instance, on crops. But this, we are not yet starting investigating it in Africa, for instance. There is an impact of air pollution on our buildings. We have not yet started an investigation for now. We are not yet started. We know that in our remote areas, we have these mining companies who are jigging almost every day. They are selling tons of dust in the atmosphere, but no one is there to investigate. And there's no law that have been adopted against this. Also, we know that there is an interaction also between the climate and air pollution. This for sure. There have been a project called the Dasiwa project. That was, I think Julien, who is here, knows better than me because he was part of that project. But I discussed with the leader of that project a couple of years ago in 2022 during a conference, and he sent me some publications, and he gave me the conclusions of this Dasiwa project. And one of the conclusions is that the air pollution is affecting the climate in West Africa. This is one of the conclusions that he made. And this is for sure, this is demonstrated. They took the aircraft and they made some measurements in high altitude, and they came to that conclusion. And they send the conclusions to the policymakers. So they are the one to react now. So what are these policymakers doing at the moment? I don't want to say nothing because there are things going on in Africa from what I know. I am in contact with some colleagues in Ghana. I know that in Ghana, for instance, they have passed a law that was a couple of days ago. They passed a law because in our constitution, is our laws, we talk about the protection of the soil, protection of water, of the forest, but not of the air. It doesn't exist in most of our laws. This does not exist. So it's just now that we are trying in many places in order to set some standards. So in Ghana, for instance, they have put a bill in the parliament for that. In Senegal, we have adopted, that was a couple of years ago, a law also, some standards here in Senegal. But when we look at those standards, we didn't know what was the process in adopting that standards. It seems that in the Ministry of the Environment, some people sat there and they decided. We don't know how they decided. I know that in South Africa, for instance, also they're also working, adopting some standards that will be more concerned for companies. You know that in South Africa, for instance, they have these mining companies, Eskom company, who use coal to produce electricity, and they have polluted a lot of places there in South Africa. And this has been a lot issue, a battle in the court with some corporation.
That's a good point, actually. Like the lack of laws in constraining laws in Africa to constrain all the companies to have similar standards like EU, for instance. Let's say if you take the gas, oil, whatever, in EU, they have really quite clear standards. You cannot exceed certain type of size of the amount of, for instance, the NO2 or whatever, like the NOx and so on, that are really creating health issues. But or the sulfate, whatever. Based on that, actually, you can see the oil gas in West Africa is really highly polluted compared to the European standards. And it was like, there was one paper in 2020, second is that it was looking at the dust aerosols impact in West Africa. But they realized that how the dust is impacting the health, the standards that they realized was not the same like EU. And this, I think, what we should do, like in the government level or in the NGO levels, to force the government to take decisions that to constrain this, because it's kind of, when you're Africa, you can pollute everything what you do. Yeah, there is no constraint. Then they say, we do what we do, like we don't care that much. We just want to make profit. And if there is more constraint, then they need to to adjust, because if you take Total, for instance, making 85% of the benefit in Africa, why? It's probably due partly to the fact that they don't put too much effort of getting the standards of air pollutions similar to EU that cost a little bit more money to reach that.
Yeah,
this is my question. What should we do? What should we do?
I think I can follow up a bit with the discussion on air pollution, because I was really surprised when you showed a plot, I think about PM 2.5 or something, that showed that Africa is kind of very, very red. I mean, because from a long-term climate change point of view, there was really no pollution over Africa. At least it was not accounted for in the past. So if you look at the West African monsoons, the drought of the 70s and 80s, and then the recent recovery, I think what we learned from the literature is that was mainly driven by pollutions over Europe and North America in the 70s and 80s. And just allow me to land. And then when they had the Clean Air Act, and then again, you really have to talk about specific things, because I'm talking specifically about sulfate aerosols as a representative, which is like a very big impact on the climate from the CIMI point of view. So sorry, I'm talking about something that is specific. So yes, so these sulfate aerosols. So I was surprised when you showed this is something that is interesting going forward. But what I think is that a lot of what you show, because we are talking about how climate change impact, how climate change affects pollution. But what I think is really like pollution affecting climate change on the very long term.
But feedback, I think this is a feedback effect for me.
Yes.
Yeah, but the problem, because you're not talking at the same level. Like the feedback effect is that what the pollution, the sulfate emissions and so on is doing to climate in large scale circulation. And then you have like the local, how we can say, the tropospheric, like the countries in, the city pollutions, there is a little bit different. It's two kind of scales. Doesn't mean that the city pollution doesn't have kind of feedback effect to the local climate and precipitations, especially, and so on, also on the health. The SS2 is more global, like the sulfate aerosol is like the global effect. But I think what he pointed one point, which is important, which is lack of observations.
Yeah.
This is really one of the I can let you avoid.
Yes, what you ought to know is that is very important, is that we as African scientists, we have a lot to do, because in the science arena, most of data on Africa are missing, or either are wrong. Most of them, all parts of science, including ecology, medical science, and so on. Most of the time, they are mistakes, they are biased, and you know that most of the time. So that was back in 2010. I was working on energy, for instance. Okay, I was looking for statistics on Africa, on the world, and in order to know how is the energy produced and how is it consumed around the world. And I found out, for instance, in terms of capacity installed in Africa, they were talking about 1 gigawatt in 2010. 2015, 1 gigawatt. I said, no, I am in Africa. I'm seeing how we are building the dams here. We are building power plants here, but they cannot say that it's the same data. So because sometimes they make assumption, they just put the data and then they end there. So most of the time, they are wrong. And before 1960, I am not sure that there were data that were available. They made an assumption, and then they say, okay, we continue. But just of recent, when we started doing this research, producing data, we realized that in the global south, we underestimated the pollution. This is what we realized, that the levels were very high, higher than what we were estimated at that time in the 60s or the 70s or the 80s. We used to say, no, Africa does not have industry, so they are not polluting. That's not wrong. That's completely wrong. That's completely wrong. Now we know the real data now that Africa is polluted, and we know why. We are knowing why now.
Yeah, so can we invite Jonathan? I don't know if he's still there, and Carl also. Carl, are you there?
Yes, I'm here. Yeah, I basically agree with everything that was said. One thing maybe to add in terms of sort of data sparsity, there's, I would say, a lot of potential for satellite data to be useful in filling in some of these data gaps in regions without local information. However, there's always the challenge and the caution that these data sets may not reflect local conditions because they're measured from space, and there's a lot of assumptions being made in translating that to local conditions, which may not be applicable in specific contexts. I know there's some discussion going on in the chat about this very issue for hydrology modeling in particular. So I think there's, I guess, yeah, I'll probably leave it at that. There's certainly potential in exploring the use of satellite data for filling in these gaps in observational data, but it's not on its own. It's certainly not a solution, and it has to be combined with what local information are available to really address the issue.
So, okay, Eric, you want to add something?
Thank you so much. Will not add a lot, but one of the things that I may say that as we are looking for the future of the continent, so there is really a very high need of cooperation between especially the government, like. Starting to the example of my country, really most of the people, they know that Rwanda is clean, especially when it comes to Kigali. But Uganda-wide, we have also air pollution with high. Some of them, it's like most of the things. You'll be finding that the data that I'll be using to analyze will be taken probably by some satellite, and we need also to come up from the satellite and also come to the ground to pick some data from the ground, not only from the satellite, and then we compare those data from the satellite and also the grounded data together. I was last month ago, I was in Kenya, and Kenya. is not clean when we go for about city which are clean and Nairobi. And one of the things that I find that I said, why do we have probably air pollution which is higher than Nairobi, yet we know that our city is clean? Also, the demography, if I can, the geographical location of different countries in Africa, so require also the attention for a very specific. Like my country is full of hills, and sometimes the air pollution, when it comes, it's really like a dump. When it can go out of that dump, because it's like among the mountain or among the hills, so then it will continue to circulate there. And then we need to think on something that my country already is starting working, where now we have the Rwanda is having the partnership, I don't remember which country, that is going to start selling them the CO2. So we need to start now to explore and looking the way that those pollutants, we can also capture them and then we produce or we use for the other things. Otherwise, I can say that I will reshape my country, because it's a country of hills and there's no way. And also we have to have those industries. We have to have all those other things which would be not good for the climate, but in order to come up, so we need to take some measures that will be very strong. And we encourage that the government, especially in Africa, they need to work together. Like in Europe, I'm sure that they usually used to have the way they correspond when it comes on climate things. But when it comes in Africa, I don't think that we have that kind of moderating or looking how the things are going. Thank you so much.
Okay, thank you, Eric. We have a question here from the participant. You can take it.
Thank you. I just wanted to talk about the concerning the sources of air pollution in Africa, especially for the Sahelian countries, so the countries which are near the Sahara Desert. I just wanted to talk about one of the sources of air pollution in Africa, especially for the Sahelian countries. For example, around the month of December here in Senegal, there are some announcements that are telling us that there is dust in the air coming from the desert of Sahara, which are coming, and we are recommended to wear face mask. I just wanted to talk about the other source, which is natural. That I saw some countries which are planting trees from different sizes near the desert, just to mitigate the level of dust in the air coming from there.
Thank you. But now we want to give an answer.
Yes, I can elaborate on that. On my presentation, I didn't want to talk about the sources. I'm sorry for that. I don't know why I was hesitating. I wanted to put one slide, but later on I remove. Well, there are several different two groups or two categories of sources that we have. We have what we call the anthropogenic sources. This is man-made, okay? When you drive your car, when you are cooking your food, okay? So we have those sources. Even when you are sick, you release viruses and bacteria when you are sick also. So these are some sources that we call, let's say, anthropogenic, so man-made sources. But these are most for activities. And sometimes we think more about industries, okay, releasing some of those pollutants. We think about the transport systems, okay, about cooking activities, and so on and so on and so on. So we have man-made. But we have also at the same time some natural sources. And as you said, we have this Sahara, this desert. Because desert, not only Sahara, desert in general, because they are empty spaces, they have a lot of sand there most of the time. And when there's a strong wind, it carries all those sand, and we have the dust storms in some areas. And as we know from the Sahara desert, for instance, here it is between December, January, March. We have this episode of dust here in Senegal. But sometimes we can have them elsewhere also in south of Europe. And that dust goes very far till in Brazil, in US, in part of US also. It's not just here, localized here in Africa. So this is one of the reasons why you see sometimes that those countries who are close to the desert, like Niger, Chad, and so on, they used to be very polluted when you see the data. Okay, this is one of the reasons. So apart from this desert, we have also the pollen. When you have crops, okay, we have those pollen produced by fruits. So that are carried out by wind also sometimes, and this is in the atmosphere also sometimes. So we have that, and we have also some bushfires when people are producing are cleaning the floor for agriculture. Okay, we can see sometimes that from satellite data that we are seeing those particles produced from those areas where people put fires and set fire and so on. We have also what we call the sea sprays when you are close to the Atlantic coast. Okay, so there are many sources like that. Okay, that exists also in the atmosphere also. So these are what I can say. I think Carl, who used to work also on this kind of topic, will say something about the sources. Carl?
Yeah, I mean that's a good summary, and again, many of these sources are also I showed an example in one of my slides of the different sources, the different types of aerosols, basically simulated in the model, and maybe I'll try to find the animation. But there's an animation that kind of shows these sources, and you can kind of see the biomass burning, the dust. Saharan dust is certainly a major source. As was mentioned, and sea spray as well near coastal areas. Pollen, it's very interesting that you brought that up. That is something that's not currently captured. These biological aerosols like pollen are not simulated in the current version of the models that we run. So that's an important limitation if you're thinking about the impacts of things like pollen. I know there are efforts ongoing to kind of simulate those, but as you can imagine, it involves both. It's somewhat more complicated because you have to consider both the behavior of the plants, so you have to model the biology of the plants as well as the atmosphere itself. So there's more coupling there to consider. Yeah, maybe I'll just leave it at that. But yeah, there's certainly natural sources of aerosols. And anthropogenic sources, and then there are sources which are maybe a little bit more of a gray area. So you have combustion, burning. Some of that's natural, some of that's caused by humans, and maybe there's some gray area, especially in areas like the United States. There's some fires, but are they natural, or are they caused by humans? Or are they caused by climate change and making the fires more frequently? There's this gray area of what you want to classify the source as. Yeah, I think I'll maybe leave it there, but those are the two comments I wanted to make.
Thank you. Maybe so I have a question for Bertrand. So what is the level of collaboration between research institution and the Met service? I think we have the opportunity to have here Mori. I don't know if he's here. So what do you think? Because the Met service has a mandate to collect data, to provide climate information, and this is to help us to understand the process.
Well, this is a question that keep coming every time when we have meetings. It keeps coming. 3 years ago, we were in Ghana discussing this topic of equality, and there were some people in the room coming from Ghana EPA, and there was this debate because the researchers from Ghana who was in the room, they were very angry with that agency because we don't understand why sometimes there should be a kind of misunderstanding or lack of collaboration between researchers and those agencies. We are working as in the public universities, and they are working in public agencies, but we cannot collaborate sometimes. And this is a pity that it happens like that. Okay, but what we want to collaborate with them, and sometimes it works, sometimes it doesn't work. In Ghana, they have made some efforts in order to be in collaboration. In South Africa, they are making this effort. In Nigeria, they are making this effort. In Senegal, so far, they still these things. Maybe you know better than me. They still distance with them. I don't know why. Just a couple of years ago, I had students that I was supervising with a colleague, and we wanted data from ANASIM. And we said, okay, let's go to ANASIM and ask for the data. And when we went there, they asked for money. They said, oh, a public agency asking money to a public body. It doesn't make sense, but this is what happened. They told, oh no, you have to pay for it. It's strange, but this is what happened. And we're very surprised that it happens that way. So what I'm trying to do these days with some colleagues that are working also on air quality is to try to meet and try to see how we can collaborate better with those agencies, because there are many, not only ANASIM and so on, there are many like that, but there's lack of collaboration when it comes to Senegal. From what I know, this now is not, we are not very close. But elsewhere in Nigeria, as I said, because I talked to them, I discussed with them, and I know what's happening there. In Francophone countries, it's very difficult. In English-speaking countries, it's better. This is what I realized. I don't know what's happening in northern countries. Maybe someone here to tell us, but I don't know. But in French-speaking countries, it's very difficult to see collaboration between universities and university or research centers. I don't know why. I don't know. Maybe it's a matter of culture. I don't know. So we need to find a way to solve this problem. Yeah. Another question?
Yeah.
But go. You want to?
We are running out of time. You are ending very late because we have another session. Okay. Yes.
Okay. Thanks. First, I want to say something about the collaboration with the research or the meta agency or the another agency. I think the thing we say is the true because in we have some lack of some. This is the problem of I think it's a problem of finding of more than, because the meta agency say we need more money to have the data. The institutional researcher need data. I think freely it is just some problem of founding of but I think we can solve it with better collaboration, have a convention of something. I think we can better solve this problem. The second thing I want to say is we speak about the company or the I think the industries we pollute our environment, and you say you can make the law to I think to contrast them to have some I think some mitigation of pollution, and I think this company it can help for the research. For example, we speak about the gap of observation. We can contrast this company to help the agency or the research to have some sensor, to have some observation to permit already to study about the air pollution, and after we can develop I think some air quality monitoring or air quality forecasting. I think this company we can contribute, and we need to oblige with law and this thing to contribute to this thing, because it is the source of pollution, and this company have much money. For example, the cemetery in our country, we have much money. We can contribute to research, to developing monitoring and forecasting system for air polluting. I think we can manage it. Thanks.
Thank you. Many challenges. I'm wondering if in global north we have the same problem, the same thing.
Thank you. I have a question for Eric. Thank you for your presentation. What I see recently in Kigali, to improve the air quality in Kigali, the government implement a system of Sunday no car. I would like to know if you research actually you have observing the impact that the measure has had in the reduction for air quality. Thank you.
Thank you so much. We actually every first Sunday of the month, and sometimes the third sometimes, not every time, third week of the month, we usually need to have what we call car-free day. And the car-free day, that means in the whole city of Kigali, no cars are going to move. Few they are going to move, but mostly everyone will be engaged into sport, the group sport, where we do on the different point station where we do the sport and the groups. So I was leading one of the paper of my colleagues who are working on. He's in America actually. He's doing his PhD. He did a research on that, and then I was reading his paper just today morning, and then he was talking about the impact of Car-Free Day in Kigali City, and it's related to the air quality. So it has improved something, but it's still there's still a long journey, because we are talking. One of the things that I talked previously is that there is a problem of having our country is hills, as I said, and sometimes the air pollution will be remaining, circulating there around. So having the Car-Free Day, of course, the reduction of that air pollution which is coming on the cars is going to reduce. And another thing that you need to know is that Rwanda, we are trying to implement the electrical cars in different areas. So we are trying to be the lead, of course, of in Africa, but still the journey is still long. When you go outside, then you measure, still you find that we are still having a lot of journey. So there is a little bit percentage which has been done on that, but the journey is still long. Yeah, thank you, Carl, for putting the article that I was mentioning. Yeah, that's the topic, the paper that I was reading just this morning, because there is a paper that I'm writing on, so that I have to submit by tomorrow. So, and during the reading, so this one also was interesting. Thank you.
Great, thank you so much for that insight. Moha, what's happening, sir?
I think we need.
I'm trying to end it, but there's an echo. Whose mic is it? It's your phone. Okay, great. All right, so I just wanted to quickly respond to an earlier comment that was made, and then maybe ask a question that we could all answer very quickly, because Moha wants us to go to break so that we can begin our next session. But I just wanted to comment on the earlier statement that that maybe you're not collaborating very well across the African continent, and that it seems that many other places are doing this very effectively. And just to say, in the US, it might seem like many groups are collaborating and they are doing so effectively, but not everyone collaborates effectively. I mean, there's people that I work in the same building with that I don't end up collaborating with effectively, right? So you kind of have to, I would just suggest finding your own groups of people that you end up working well together, and then be productive in that way, and acknowledge it's not going to work well across all institutions and so forth. So on that note, what do you think we could try to collaborate better, both for you within the continent of Africa and maybe beyond, for those of us that are living outside of the African continent? So I'll let maybe Eric, you can go quick, and then I'll pass the mic here.
Maybe we take the last question, and then before we close,
Thank you. I want to come back that I don't know his name, say, I think the rule is for the minister or for the government. You know, when I go to the one decisioner and I say him, PM 2.5 has classified as group 1 on cancer region. This is a great thing. This is you know, PM 2.5 can affect our heart, our blood, and even our brain, and it is a issue of public health. You know that when ANACIM or the Center of Centre de Gestion de Qualité de l'Air needs a funder. The government must help us to have this funding, because after the problem is a half public health issue that I want to add. It is not, I think, for my side, it is not, the problem is not ANASIM or the other center. It is the government to take and help them to have some monitor. You know, in Dakar, we have 8 sensors to collect, to measure air pollution. And me, I work with some models to help to estimate and predict PM 2.5. When I go to the center and say him, you have 8 sensor, it is not enough. But when you give me data, I can help you to predict or to improve your prediction. This is a collaboration, and the impact of our research is a help to the decisioner to take some decision if he need it. That I want to add. It is a real problem to have data here in Senegal from my side, but we need to find some solution for this. Thank you.
Sit down. Go ahead, and after you have to.
Okay, so well, I will come back again to this issue of collaboration between agencies and research centers. It's not that easy. It's not that easy to manage. We have been trying for so many years to collaborate with people. It's not easy. Sometimes somebody is appointed, is open. Another I was appointed, is also open for the door. So we don't know exactly how to do with that. I don't have the solution. Maybe God has, but for me, I don't have a solution now for that problem. Now, concerning the industries, well, most of people, decision makers, they don't know how works the industry or the economy most of the time. You cannot just go to the company and tell him, put the monitor and enforce the law. No, it doesn't work. I'm a manager of a company. You come to me and say, okay, please, you have to reduce the PM 2.5 that you are releasing in the atmosphere. Otherwise, I will put a fine. How will I write? I'll say, okay, put the fine. And when you put the fine, I increase the price of the product to take my money back. This is how they work. It works sometimes. So it's not that easy. In order to manage with them, there is a process. Talk to them, explain to them, put a schedule so that they can follow gradually. This is what sometimes we do. But it's not easy because they don't care. They don't care. They're there for money. When I open my company, it's for money. This is how the managers or those who have companies behave. They want money, finish. The rest, they don't care about the rest. It's just when the state is very strong that the state can impose on them sometimes. But even there, it's not easy because they used to know how to manage. They go to the parliament, they corrupt people there, and they blow the law. We know how they do. So it's not that easy that way. This is to answer you. Now, coming to the collaboration between Africa, well, it's not easy. It's not easy. I've been trying past 5 years to put in place what we call the African Society for Equality in order to bring researchers together in Africa. But it's not easy. Why? Because if you want to set it and never like that one, you need people who are volunteer. Okay? Because you don't have money to pay them, of course. But sometimes it's difficult to find people who will be volunteer to come to the meetings, to come because there is a meeting or we need to decide on this. It's not that very easy. But what I believe is that, but gradually, with the time, when you have the critical mass of people or researchers, this can easily happen. Sometimes, when we started this society, African society, we are doing some activities, okay? But when we started, we were something like 20 people. After some point, we were 60. After 100, now we are 200. So it means that in Africa, We are having a big commission on air quality now in Africa. And I'm sure that in maybe next year or in 2 years from now, we are going to have this established, because I was expecting to have more and more people. Now that we have that people, most probably we will find 2 or 3 people who are ready to work for it, okay, and we put it in place. No, now, something that hindering collaboration in Africa, there are many issues. This morning we're talking about visa issue. It's not easy for me to travel because I need a visa sometimes. Even within Africa, it's not just when we are going to a road. No, even within Africa, it's not easy to get a visa. I myself have tried to invite some people here in Senegal, but it was not easy for them to get the visa. So we have this visa issue. We have the issue of funds. We need to look for money to invite people for collaboration. We need projects. And I was just couple of days ago in Italy. We were discussing about physics education and research in Africa. And I was telling them that we need an African Science Foundation that will put money there and to sponsor research in Africa, to fund research in Africa, because we don't have. At national level, we don't have. At regional level, we don't have. But maybe if you have something like an African Science Foundation, maybe we have money, maybe we don't know. And for a country like Senegal, I used to say it's not normal that in Senegal, you cannot, the Ministry of Higher Education cannot put $1 million per year for research. They cannot put. But I don't understand why. Because for them, it's not a priority, research. If you put only €1 million per year, it can do a lot in this country. Senegal will become a superpower in research. I'm sure of that. €1 million just per year, but they're not doing that. Why? If I have €1 million today, I will do enough of things. Instead, I say, okay, you veteran, take 10,000. I will say, okay, I have a friend who is in Ghana doing equality. I will invite him because I have money for that. But if they don't sponsor, what are you going to do? Since 3 or 4 years now, I wanted to organize a conference here in Senegal, but I need somebody to sponsor. Who can sponsor? I cannot do it alone. So we have this kind of issues, but progressively, maybe this something can be, they should be so maybe in the future, but we are going progressively, you know. Thank you.
Okay. Thank you, Professor, for this great discussion. So we have to close this. But yeah, it is not a break, but we have that is a break, and it's not a break. Yeah, right.
No, it's not a break.
Yes,
No, it is not the break. The break is at 4:30. We had a presentation from Dr. Birgit Hessler. She will talk about the ECMBAL tool, and then we have a follow-up of hands-on section with her, how to utilize that for CMIP 5, CMIP 6, CMIP output models compared to ERA 5, and so on. Yeah, so you are not now in break. You wait 30 minutes before coffee break.
Just a quick question, Moha. So hi everybody, I'm here. I was wondering if we could have the break now, because it would be nicely, we can go nicely from the presentation into the hands-on session, if that would work for you.
Yeah, just
for us as well.
Just wait. Then we have to check outside if they are already settled, because it's not based on us.
I see what you mean. Yeah.
Okay.
So is Moha checking?
Yes, you want to check.
Okay.
Yeah.
So during this time, I can introduce myself very, very briefly. Hi, my name is Birgit Hassler. I'm from the German Aerospace Center in Oberpfaffenhofen, which is close to Munich. I will give you the introduction to ESM tool, which is a software package, and I will talk about this a little later. But I also want to introduce you to my colleague, Bettina Gier. Tina, switch on the camera and say hi. So because she will give you the hands-on tutorial, introduction to the tutorial later. I'm very sorry we can't be with you. I would have loved to come to visit, but this will have to do.
Okay.
But it looks you have a good crowd.
So they will be ready in 15 minutes. They will be ready in 15 minutes because I mean there was time to 4:30.
Yeah, that's fine.
Yeah.
I can start with the presentation, then we can have a break in between. I'm easy. So, or I can do the full presentation now, then we do the coffee break.
Yeah, let's do it like this. Yeah, if the presentation is about 20 minutes or how much was it again?
I had an hour, Moha, so I have prepped 45 minutes of presentation, but I can shorten it if you want.
No. I mean, you have your whole time. I was just wondering, like, if you cut in between, and they come back with coffee, they will forget where you are.
That's right. No, I'm easy, so I can fit it in about half an hour. That's fine.
So Birgit, maybe we can do it like this. So they will be ready in 15 minutes. In meantime, 15 minutes. They will be ready in 15 minutes.
Yeah.
So this means anyway, you have to. We'll not finish at 6. We'll finish maybe 6 something. So what
no, that's fine. As I said, I'm here. We can. Tina's available. I'm available. We can do however you want.
Okay, let's do it like this. So let's go outside, and then in about 10-15 minutes, they will get the coffee ready. You will get some fresh air, but the coffee break will be shortened, just to keep that in mind. And then we have to come back a bit earlier.
Yep.
Is that
sounds good?
For you?
Yeah, sounds good. And then, so in about, I don't know, 20 minutes or so, you're back?
Like the 15 and then plus
15.
10 minutes. Let's 20. Yeah, in 30 minutes.
Okay. And then we start, and then we do the presentation and the hands-on session together.
Exactly.
Okay.
No stop. Yeah.
Sounds good.
Thank you.
Enjoy
Thank
coffee.
you. Yeah. I hope it is not cold there.
I'm freezing in my office. No, it's not that bad.
We'll send you the sun and the baguette.
Yes. Thank you.
See you later. So let's go for a coffee break. Just before you leave, maybe for the people from AIMS, I still need where are you coming from? And then before we leave also, we would like to first activate the mic. We would like to thank all the speakers. I think Jonathan is almost late there. Eric, yes, and all of them, all of you, Michaela, all the speakers of the day, Professor Bertrand. So let's give them an applaud. Yeah, we will come back in 15 minutes, in 30 minutes maximum. Yeah, thanks. People from AIMS, would you mind telling me here, coming here, please? I need information again. Yes, I need information from you. I need your country of origin here. Who is Emmanuel Kiri? Kenya. Yes. Everyone should be here, right? Yeah. Okay, can you write, please, faster? Yeah, actually, in advance because some of them were in here and yeah.
Done.
Yes. Before, sir, can you change something for the first name? To check.